So, okay, we are live on YouTube, right?
Yes, you're live.
Okay, okay. So I'm sharing my screen right now. Is it visible? Hello?
Yes, Debojyoti, you are visible.
Okay, okay. The screen is visible, right?
Yes, it is.
Okay, okay. Okay, so let me start. Hi, this is Devojyoti Pramanik. I am currently an electrical engineering third year student in NSCC, and I am a hardware developer and IoT enthusiast. Now, you might be thinking, how can a person of electrical engineering interested in hardware doing in this session, right? So, yes, you are right. Although I have a partial knowledge in machine learning, artificial intelligence, and neural networks, I am aware about the possibilities that these can do. I mean, it can almost give an artificial trained brain to a piece of microcontroller or anything like that. And so, what do you want more? So, jokes apart. So, as you know, I'm here to bring in front of you the miracles that you can create by combining machine learning with IoT or hardware projects. So I want this session to be a bit interactive. So you can post your questions in the chat box. Also, as the session is live on YouTube, you can also comment your thoughts on the YouTube comment section. So, okay. So what is machine learning? Let's not go much technical on this. A huge part of this was covered by Somdev Basu in our first session. So, in a layman manner, machine learning can be explained as automating and improving the learning process of computers based on their experiences without being actually programmed, that is, without any human assistance. The process starts with feeding good quality of data and then training our machines by building machine learning models using the data and different algorithms. The choice of algorithm depends on what type of data do we have and what kind of task are we trying to automate. So let me give you an example. So suppose you are preparing for a technical paper. So you don't just blindly memorize all the formulas and concepts, right? You try to understand it. Before the examination, you feed your brain with a good quantity of high quality of data. That is question and answers from different books, teachers' notes, online video lectures, YouTube sessions. So think of the time when you are giving your boards. That means class 10 or class 12. So what did you do first? You read your textbooks. You prepared the notes which were given by the class teacher. You prepared the notes which your tutor had given to you. Then at last you solve sample papers. So so there are mainly questions in sample papers. So you train your brain with questions as well as answers. So you actually training your brain how to work with input as well as output. The questions are input and the output that you will give is the answer of the following question. So each time you solve practice test papers, you find your performance by comparing the answers with the answer given. Gradually, as you solve the sample papers, the performance keeps on increasing, and you gain more confidence with the adapted approach. So briefly, suppose you are preparing a subject, and the subject has 10 sample papers. Each sample papers have 3 questions. So basically, you are prepared for 30 questions along with their answers. Just a minute. Just a minute. So actually, you're training your brain with to work with both input as well as output. So what I was saying, you have actually prepared for 10 questions, sorry, 30 questions, and as well as answers of those 30 questions. So now the question which will appear on your exam, you're quite unfamiliar with it, right? You don't know what question will appear in exam. So basically, you combine all the answers of the questions that you have prepared, form a appropriate answer, and write it on exam sheet. So this is actually how models are built. You train the machine with data with both inputs and outputs, and when the time comes to test on data, our model scores by comparing its answer with the actual output which has not been fed while training. So that's what machine learning is. You can refer to the session which was taken by Somdev in the first day. You will have a better idea on this. Now, what is IoT? So IoT is a system which consists of sensors or devices which talk to the cloud through some kind of connectivity. So once the data gets to the cloud, the software processes it, and then it might decide to perform an action such as sending an alert to the alert or automatically adjusting the sensors or devices without the need of user. It is also a way through which you can make your existing non-smart devices to smart devices. So let me give an example on this. The most simple example which you can imagine right now is smart homes. So for a clear-cut idea, suppose you will be automating your room or your home. So you want that all the appliances or lights must be turned on by clicking on your mobile once. Just I mean, suppose you will be automating your home so that you can switch on lights, fans, ACs, various appliances with the help of a web app or a smartphone. But you don't want to make a huge investment on it. See, the smart bulbs and the lights and the smart ACs which come requires a huge amount of money. So replacing all the light bulbs, all the appliances, all the non-smart appliances with smart appliances can be a huge task, and it will uh, and the budget will be much more than what you have expected. So now clearly you don't want to make a huge investment on it. So what you do is connect a relay to the switches. So let me briefly explain what a relay is. Relay is actually a automatic switch, electromechanical switch. Actually, for simple words, I will refer to it as automatic switch. So whenever you give plus 5 volts or signal to the relay turns on, and when you remove that signal, the relay turns off. So we basically connect the relay to the microcontroller, which has a Wi-Fi chip. This is the most important part. The microcontroller should have Wi-Fi chip. So you basically program the microcontroller, take help of any web service which will allow you to access the microcontroller remotely, and your home is automated. With the click of a button from anywhere you of the world, you can switch on or off the appliances. So this basically a simple thing. I hope you can understand. Just like Google Home and Alexa. When you tell Alexa, Alexa, switch on the lights. Google, okay, Google, switch on the lights. The lights gets turned on. So you don't have to make such huge investments to buy a smart home speaker like Google or Alexa, and then buy smart bulbs and then link it and automate it. Just you simply connect a microcontroller, program it, take help of any web hosting app, build an application or build a web app, and then simply control your devices. As simple as that. But you have to have a knowledge of IoT. Now, let us come to the main point. What happens when you combine machine learning with IoT? You are actually giving a trained brain to a device. So defining this thing is a complex task, and if I do, many of you might not understand it. So let me explain this thing only via examples. So let us suppose I have a bunch of bananas and apples, and I've got a sophisticated nano camera and sensors to collect the data from these fruits. If the data collected by these elements is fed into my laptop through the internet, my laptop will start analyzing the information by using sophisticated data analysis software and the cloud platform. Now, if my laptop shows graphically how many bananas and apples I have left there, so my system is trained, and I have put an machine learning algorithm in there. So my system is able to differentiate how many bananas, how many apples, and how many oranges are there. So the part where let me get a marker here, pointer. So the part where the sensors and the camera are collecting data and sending to the cloud, this whole part is a part of IoT. Okay, and the analysis and the computing part, which helps the machine to distinguish between the fruits, is a part of machine learning algorithm. But this does not end here. As you know, possibilities are not limited. So if my program is able to describe graphically how many of these are now ripe to be eaten, so let me take here an example of mangoes. So if my program is able to graphically describe how many of the mangoes are ripe enough to be eaten, how many they are not quite ripe, and how many they are raw, it proves that my machine has learned enough and has become more intelligent. This part also depends on how we have trained the program to distinguish these. So basically, the sensors take the data from the picture or the fruits kept here, and it sends to the cloud. Now the cloud, using a machine learning algorithm and sophisticated data analytics, distinguishes these fruits of which are raw, which are not quite raw, and which are ripe. Okay. So the question comes, what we will do with these results? Okay, I took the data from sensors, I distinguished it that these many are raw, this many are ripe, and these many are half ripe. So what will I do with this? Innovation comes here. Now, as my computer is able to distinguish between these fruits, let me attach a mechanical arm to the controller, which will automatically pick up the ripe fruits and keep it in a box, pick up the raw fruits and separate it from the stack, and pick up the medium rares and place it in a separate place. Okay, so actually you programmed this mechanical arm to the computer actually detects how many of these are raw, ripe, and half ripe, and this mechanical arm classifies these keeps these raw mangoes in a separate place, partially ripe mangoes in a separate place, and ripe mangoes in a separate place. This is how you combine machine learning with IoT. Now there are many applications. So this is actually a simple concept. So you can apply this in suppose let me give an example. Suppose in factories such as Maza, Fruity, so these deal with mango pulps, right? So a huge lot of mangoes come daily from the garden to these factories. So if you keep this machine here, it simplifies. The machine can take the job of 7 men and with a greater efficiency. You are basically replacing manpower with a machine with a greater efficiency. Suppose a man is able to sort out 700 mangoes in an hour. This machine will instead sort out 7,000 or 70,000 mangoes in an hour. So that's what the power lies in here, combining machine learning with IoT. So there are many applications in healthcare. So suppose we have designed a band which consists of array of sensors which will measure the which will measure the patient's heartbeat, heart rate, the temperature. So the raw data is transmitted to the patient database in a cloud platform. Then the doctor can access the raw data, the previous prescriptions, etc., using sophisticated machine learning algorithms and recommend specific drugs to the patient at remote places if required. Thus, the patients at home can be saved from life-threatening health conditions such as sudden heart attacks, paralysis, etc. So these IoT devices will contain nanosensors which will be attached to the skins, and the data will be taken from here. This data will be then be sent to the cloud, where the machine learning algorithm, classifies machine learning algorithm, classifies it, and then the doctor can serve the prescriptions to the patient, so that the patient is out of danger. Now, these are literally simple things. You might see these products in markets. Now think apart. Now think of what type of miracles can happen if we combine a really advanced machine learning algorithm in a sort of field to a very powerful microcontroller. Just imagine the possibilities. So some examples of projects in machine learning and IoT are in space projects. NASA is using the similar technique so that rovers can take samples and the data effectively. In both the lunar and Mars projects, NASA is using hardened sensors that can withstand extreme heat and cold, high radiation levels, and other harsh environmental conditions found in the space to make the machine learning algorithm of the rovers more effective and hence increase the lifespan and reliability. So today an aircraft is equipped with thousands of sensors, and the machine is so well trained that it can take major decisions itself during an hazard. Today an Airbus aircraft is provided with thousands of sensors to measure temperature, speed, fuel consumption, airflow dynamics, mechanisms of working area. All these data provided by IoT devices is connected to the cloud. Cloud platforms such as IBM Watson, Microsoft Azure, etc. via the internet. Using these sophisticated data analytics, useful information is fed back to the machine, that is the aircraft. Using this data, the machine can learn very fast to overcome its problems so that its lifespan and performance can be greatly enhanced. So there are lots of IoT projects that you can find on internet. You can similarly do them. You just need to collect the hardware related to those. Similarly, there are hell lots of ML projects that you can do if you learn it. So let me give you some examples where you can combine both of this. So let me give an example of water filtration system. So you design a water filtration system which filters the water as well as takes the samples. Okay, so there are several sensors as the TDS sensor, that is total dissolved solid sensors. pH sensor, I hope you know what pH is. So these sensors collect the data and to feed this data into a machine. Okay, now suppose you are applying this data to we are applying this machine to anywhere in suppose a river side or beside a lake. You take the water sample, filter it, and take the readings from them. Then with the machine learning algorithm, you can predict what type of vegetation can the area beside the pond have, or area beside the lake, or area beside the river have. What type of future industries can you set up there? The type of land, the vegetation which can prevail there. There are many things that you can do by combining IoT with machine learning. Now, the traffic light based system, I think you are well aware of this project because I think Somdev has also done this project. The traffic light system actually consists of a camera which determines which is trained by the traffic which is prevalent on roads. By getting the amount of traffic on roads, you can prevent the traffic jams there by controlling traffic lights using the help of machine learning. So this is an example of machine learning combined with IoT. The biggest example is self-driving cars. You can yourself build an RC car equipped with computer vision and with a trained machine learning algorithm so that it can self-drive. It will not only contain IoT, but it will contain a big chunk of robotics. You know, the motor controllers, the servo controllers, the gearbox-based system, and systems like that. But combining these two can be a difficult task. Suppose you are doing a project in which the hardware is a controller or an Arduino or a Node MCU or any microcontroller, and the ML algorithm is running on your laptop or PC, desktop. I mean, the setup either becomes non-portable or too costly. So you have to attach a mini computer like Raspberry Pi and use serial communication to communicate with the microcontroller. And suppose if you are planning to make an innovation on an existing project which is already present in the market, you see the price of a prototype shoots up unfortunately, and nobody will buy a product which will be expensive than what is already present in the market. Now let me tell one thing, that imagination is most important. We are limited by the technology present around us, but not imagination. See, I've been doing a lot of projects from a really long time, and also let me frankly speak, I have faced more failures rather than success in doing these projects. And I am not upset about it because these gave me experience. It taught me what not to do rather than what to do. So if you can visualize it, you can definitely make it, either by hook or crook. It may take days, months, years, but if you believe that this can happen, you will eventually find a way of doing so. So how many of you think a real life Iron Man can't exist? For both the audiences who believe or don't believe, I'm giving you two YouTube channel names. That is The Hacksmith and Alex Labs. Just surf through the channel and you can see what they're on to. You can understand how innovation comes from an imagination. So see, if I design a product, before the tech aspect comes the imagination. I mean, how your product will work, what are the limitations and all. Visualize how your product can work and how it can be helpful to the society, to the people. That's the main part. So since tech can be learned, but imagination can't. Imagine, research and build. That's all I say. So thank you for your patient hearing. That's all I have to say. So I'm stopping my screen share now. I think Somdev or Shubham will take the session after this. So thank you. Somdev, are you here? Okay, so if you have any questions, I actually have a Q&A session after this. I mean, after 5 minutes. So the next speaker will come in 8:50 or 9 p.m. So if you have any questions, you can drop it in the chat box or in the YouTube comment section, those who are live on YouTube. And if you have any queries, you can ask it too. Okay, there is a anonymous attendee which says repeat the apple banana example, please. Okay, so let me open the slide here. Just a minute. So which one do you want? The with the robotic arm or without the robotic arm? So just a minute. So, okay, with the robotic part. Okay, okay. So okay, okay. So here you are seeing a bunch of mangoes. Okay. So suppose you are collecting mangoes from a garden, and some of them are ripe, some of them are not ripe. They're absolutely raw, and some of them are partially ripe. Okay. So I have a camera and some micro sensors. Suppose the color sensor, the RGB sensor, sensors like that. There are many sensors. You can find the list out from the internet. So there are many sensors. You actually take the readings from the sensors and take the image of these mangoes. Okay. So you take all these readings and upload it in the cloud. So what's in the cloud? Cloud contains a machine learning algorithm with sophisticated data analytics. So what this ML algorithm does is collect all the data from the sensors, which I've already sent to the cloud, computes it, and says that these amount of mangoes are ripe, these are not ripe, and these are half ripe. Okay, suppose you divide this whole thing into an array which contains like 5 cross 4 array. Okay, so the mangoes which are present in 5 1 5 2 5 3 are ripe. The mangoes which are present in 1 1 1 2 1 3 1 4 1 5 are not ripe, and the rest of the mangoes are ripe. So what this cloud algorithm does is instruct this robotic arm via microcontroller. This microcontroller can be of any type: Arduino, Node MCU, Arduino Mega, Arduino Nano, anything like that. So this machine learning algorithm instructs the Arduino, which in turn instructs the robotic arm to pick up the mangoes which are present in 5 1 5 2 5 3 array and keep it in a raw stage. The mangoes which are present in 1 1 1 2 1 3 array, keep it in a ripe stage, and rest of them in partially ripe stage. You know how a robotic arm works. It consists of servo motors and a bunch of motor controllers which actually work as an arm. Actually, you are inserting an arm into the bunch of mangoes and keeping the mangoes which are identified by ML algorithm which are ripe into a basket. those which are identified as not ripe into another basket, and those which are partially ripe into another basket. So this is how IoT and machine learning works. This whole part is a part of IoT. Okay, you collect the data from sensors and upload it to the cloud. This part is a part of machine learning, where algorithm is present, and it detects what mangoes are ripe, what mangoes are not ripe, and what mangoes are raw. And again, this part comes the robotics part, or the IoT part, where the instruction come from the machine learning algorithm, and this in turn sorts the mangoes. So IoT, ML, and IoT. Basically, you take the image of the mangoes and sort the mangoes in a ripe manner, in a raw manner, and a partially ripe manner. So am I clear, or I will explain once more? Okay, okay. So any more questions? You are free to ask. Okay, check the YouTube session once. There is another question from Shankar Bhattacharya, that is, which sensors are needed for the water sample check? Example, please repeat. Okay, so actually there are a lot of sensors. Actually, it depends upon the parameters that you check. Suppose you want to check the pH level, you use a pH sensor. Suppose you want to check up to what extent the water is polluted, so you take a TDS sensor, that is total dissolved solids sensor. So another sensor is like that. You want to check the amount of suspended solids which are present in the water sample. You take a total suspended solid sensors. Both starts with TDS. So you might be confused on this. So there are several sensors which you can you can do your project with, that this filtration system. You can search them on the internet. You can and then based on that you search the sensors on the internet. You search the product code of it, and then you can code your microcontroller to take the readings from them. Any more questions? You are free to ask. Okay, there is another question from. So how many projects have you done? Okay, I have done several projects. I am doing projects since my second semester of my college.
Hello.
So that's all.
Hello.
Yes.
Hello. Yeah.
Yeah,
So
you're.
okay. I'm back. Can anyone make me the? Okay. So okay, I'm the host. Okay. So should I start playing the video right now?
Yeah, just turn off your own video for the moment.
Oh, my video is on. Oh, sorry. Sorry for that.
And that last question just made Devojyoti shy, I guess. The number of projects you've done. He's still working on one.
Yeah, but most of them have failed. We learn from mistakes, right?
Absolutely.
Hello, everyone. Welcome to our NeurIPS tutorial on deeper conversational AI. I am Pascal
Shubham, can you please adjust the slider to make the slides bigger?
Chen from National Taiwan University.
Just the upper slider, yeah.
My PhD students, Zhao Jiangling and Andrea Madotto.
No, the slider. Just go
This is our tutorial today.
towards the top. There is a slider.
Our
Towards
tutorial
the
will cover
right,
3 parts
extreme right.
today. Namely, part 1, conversational AI overview. In part 2, we'll dive into generation-based.
Yeah. Which one? Which one? How to make the slides bigger?
The white line you can see.
This one.
Yeah.
Okay.
Just adjust it. This is the video. Just make the slides look bigger. So towards the opposite.
Present challenges and future work of deeper
one.
conversational AI.
Yeah. Not this part. Just adjust it.
Part 1 on the conversational AI.
No, towards the left. Take it towards the left.
I'm Vivian Chen
Like
from National Taiwan
Yeah.
University.
This looks fine. Okay, perfect.
Introduce the conversational AI overview for you first, so that you can have brief understanding about the history and also the classical approach, which is usually applied to the current
audio okay?
productions.
Everything is fine.
First of all, I will briefly introduce the history of conversational AI. Although this topic is really popular these days, but they already started in early 1990s. In a lot of call center systems, they implement the keyword spotting technology. They try to identify the keyword so that they can forward you to the corresponding agent, and then you can finish the specific task based on the keyword. In early 2000s, they try to identify the intent so that the user can make the free-form text and to talk about their intent instead of the specific keyword. And more recently, we have a lot of product implementing voice search and a lot of project related to this technology. And definitely you will see a lot of production, including Apple Siri, Google Assistant, Microsoft Cortana, Amazon Echo, and so on. They all provide intelligent assistant and try to help you to finish tasks via conversational scenarios.
I think there's a problem with the video.
And then go back to you. And typical
Guys, we are having some technical operation difficulties. We'll be back within a few moments.
About slot filling, usually we'll compute the slot F major as the evaluation matrix because we have several slots need to be extracted. And for classification, domain, or intent, usually we do very simple accuracy as our performance metrics. And definitely, because we need to predict the domain, intent, and slot correctly, that means we have the correct semantics for this sentence. Then definitely we can calculate the frame accuracy as the performance of our model. And these days, although we have relatively good understanding approach, but there's a lot of trend and challenge still in this area. For example, we can consider to join predict intent and slot because intent and slot may have some correlation. For example, if we want to play the music, probably it's more likely to have the singer information or the album information in the sentence instead of the director information. And also scalability is a very important issue because sometimes originally you need to collect a lot of annotated data so that you can train your model to do the classification and tagging. But is it possible to directly extend the scalability to another language if the another language do not have rich annotation like multilingual natural language understanding? Or can we directly extend to another domain? For example, if we do a lot of in ticket, movie ticket domain, is it possible to transfer in maybe train ticket? And also to reduce the need of training data, a lot of work trying to provide unsupervised approach in order to get a better scalability. And another direction is about robustness because there's a lot of components concatenate together. But if we have the error from the previous component, error may propagate to the next component and make the worst performance. So how to make the system more robust? Like, for example, if the speech recognition generates some recognition error, is it possible to recover this error based on the understanding module? And for the second component, dialogue state tracking, the goal is trying to map the partial dialogues into a dialogue state. The input include a dialogue or the turn with its previous states. For example, we already know previous turn, the user said they want to have the 5-star hotel and also the date is equal to Sunday. And for the current turn, we know that the people number is equal to 2. So we need to check the current scenario for the whole conversation and decided we need to add this constraint into the dialog state in order to reflect the update for the conversation constraint so that we can make the search for the database. So this is the approach for dialog state tracking. The input dialog and we want to output the corresponding dialog state. And you can easily think about a simple rule-based approach. They just accumulate all understanding results so that they can accumulate all constraints together and generate a dialog state. And definitely you can think about your classification approach, which is you build a classifier for each slot and try to identify whether this slot appears in this context or not, and what is the value of this slot. However, it requires an ontology with predefined values. For example, you know you want to track the slot which is the, for example, the star number. Then you just do the classification and trying to predict whether this conversation include star is equal to 5 or star is equal to 4, and try to make this classification. Like the star value as is the classification label for your classifier. But it requires ontology with predefined value. You need to know how many labels you will have when building this classifier. So you can think about a lot of approach utilizing CNN, LSTM, and so on. For example, you can have the system output, user utterance, and then the database information, including slot and value. And you just identify whether this slot value pair appear in the current conversation or not in order to fulfill the dialog state tracking task. To do the evaluation metric, usually we will compute the slot accuracy, whether this slot is tracked correctly, and all performance for joint accuracy, like the whole frame, whether they can be tracked correctly. Definitely, there's a lot of trend and challenge in this field. Because of the limitation about classification approach, a lot of recent work try to move forward to generation-based approach. They try to generate state as a sequence. For example, given a dialog history, you try to generate a sequence represented as a dialog state, slot, and its value. Given a dialog and slot, you can also generate a value, so you can have different format setting. In this scenario, the disadvantage is you need to have multiple forward to do this generation, but sometimes it will have better performance because they may not depend on the previous slot you generated. But scalability is also an important issue, so there are a lot of work try to achieve better scalability, like multi-domain tasks. They build a lot of data set, like the most well-known data set is called multi-wizard bars. And they have several versions because people are improving this data, trying to correcting the errors or adding more annotation so that we can have better experiment and to show up the dialog state tracking performance. And also cross-domain capability, whether we can directly train on the same domain and generalize to the new domain. For example, we can describe the ontology using natural language, and hopefully we can, based on this natural language understanding, to directly transfer the dialog state tracking to the unseen domain. This dataset, SGD, schema-guided dialog, is proposed to address this task. They're trying to provide you the natural language description for each slot in the new domain. And you can, based on this natural language description, and trying to track the corresponding slot. And definitely the language boundary is also very difficult to overcome. Hopefully, we can learn in English data and zero shot on our language. For example, Cross Whistlebard is the Chinese data set focusing on similar domain like the restaurant domain, and we can utilize this data and to see the generalization capability for our dialog state tracking model. And another trend of the research direction is trying to provide different state representation. For example, you can represent your state as the graph structure, like you just consider the entity in your conversation as the node, and you have the connection between entity in a dialogue, and you want to track the structure information. And also, you can also treat the SQL query as the dialog state. You can directly generate this dialog state, which is the SQL query, and directly help you to do the interaction with the database. And another one is an excusable program, which is also very similar to SQL query, but they focus on the excusable scenario. After we finish the dialog state tracking, then we will talk about the dialog policy learning part. Dialog policy trying to design a system action for interacting with people based on the dialog states. So the input is the dialog state and also the knowledge-based result. Because after we have the dialog state, we need to search the database and get back the result. If we have the corresponding, for example, hotel, then probably we can inform the user. But sometimes we cannot search the corresponding result, and we just inform the user, or there's no corresponding hotel available satisfying this your constraint. So our output is the system action. Usually you need to design a speech act, like you want to inform or confirm or request additional constraint. And what kind of information you want to inform, like the slot value pair. I want to inform, knowledge base already returned that hotel B&B satisfying the current constraint. So dialog policy is trying to map the dialog state, KB state, into dialog action, system action. And you can directly think about, we can utilize the supervised learning and try to train the dialog state and the system action as the pair data in the offline collected corpus. However, it means that you need to collect all type of scenarios so that you can generalize to different scenario. It may not be very similar to your sync data. But it's impossible because it's impossible to enumerate all conditions. So usually we will treat it as a reinforcement learning task because it's an interactive approach. User say something and agents make the decision, then they will influence the user's next utterance. So we want to learn from the interaction with the user. So the difficulty is that we need to have a user to do the interaction and trying to build the agent to interact with the user and maximize the reward. So the reward could be task success rate or dialogue length, which is the target we want to maximize because we want to accomplish a task. So we want to finish the task and help the user. And definitely we want to make it as soon as possible. So hopefully the dialogue length can be less, and it means we will have higher reward. So our reward may consider task success rate and also dialogue length. Based on the interaction, hopefully our reinforcement learning agent can be able to get better and better capability to interact with the user. So there are so many IL-based approach to build this dialogue agent. And then you can also think about how can we do the planning in order to get better conversational system. But you know that it's very challenging that because you need to have a user simulator in order to allow the system to do the interaction so that they can update their interactive behavior and their policy. However, a good user simulator is not easy to achieve because building a user simulator just like building a system. So very important for your reinforcement learning based agent. So there are a lot of different approaches to build a user simulator. For example, you can design an agenda or you can directly learn this simulator, but it's also very challenging these days. We still cannot have the clear idea how can we build a good simulator so that we can have a better system to interact with, because user like the real human is not easy to imitate. And some trend is trying to learn the dialogue policy, just use very few annotated dialogue, and hopefully they can bootstrap the performance in the beginning, and hopefully they can better interact with the user. After the dialogue policy, then we need to generate a corresponding sentence and get back to the user. After we design the policy, which is the action inform hotel name is equal to B&B, then we just map the system action to natural language response. The agent just say, I've booked the hotel B&B for you. In the approach for natural language generation, we can easily think about the template-based approach. We just ask the expert to write the template, and we can map the template to the natural language. And this is the commonly used approach for the current products. Or you can learn how to generate this approach. And the next session, other speaker will focus on generation-based approach more. And definitely you can hybrid template-based and generation-based approach for natural language generation part. And for generation, how to do the evaluation is a big issue. For example, it's very difficult to decide how can we evaluate the current generated sentence. Can we directly compare with the ground truth reference? Or another scenario is we try to calculate the slot error rate because we have a specific slot to be covered. If the natural language did not cover this slot, then we have penalty. And then there's a lot of challenge in natural language generation part. And I think the more important part is about scalability. A lot of people trying to extend the scalability based on the future learning. For example, if we can directly utilize the pre-trained model, then hopefully we can directly transfer to another domain. And hopefully we can to work on supervised natural language generation. Without additional annotation, then we can also have a very good fluent generator to generate a natural language. So this is the whole framework for modularized task-oriented dialogue system. And the next part is about retrieval-based chit-chat dialogue system. In the chit-chat dialogue system, they are designed for free-form and open-ended conversations. We try to engage people for long conversations. But they're rare to deal with API call or a knowledge base. And usually we have two types of implementation. First one is called retrieval-based. It's very effective and also a lot of production utilize retrieval-based system. And generation-based system, which will be covered in the next session by other speakers in this tutorial. Retrieval-based chatbot, the idea is very simple. The goal is to learn a scoring function between a dialogue history and response candidate. For example, given a dialogue history, you map into a vector, and you have a response candidate, you also map into a vector. Just measure the scoring function between these two vectors. And a lot of hard work trying to train on a large set of chit-chat data, Ubuntu data, Reddit data, and persona chat, and try to map the sentence level correlation and try to provide this retrieval-based chatbot. And hopefully enter free-form text, they will automatically design the related sentence and the response for you. The pros include we can generate a safer response because the response is from the pool of the response candidates. So usually very fluent and grammatically correct because they are predefined candidates. But the cons is about the scalability issue because they have a lot of candidates you need to maintain in the pool. And also, if you want to generate the conversation about new domain, it may not have the suitable candidates in your scenario. For example, you only train on like movie domain, and currently these people talk about another domain and you do not have the suitable candidate to generate as the response. So a potential solution is you can make your model not only retrieval-based approach, not retrieved by the predefined candidate, you can generate the sentence like the response word by word. So in the next session, other speaker will talk about the generation-based approach.
The second part of a tutorial is on generation-based deep conversational AI. Let's get into it now. So this part, we will go through a This part we will introduce a vanilla sec-to-sec model for conversational AI. This is a deep learning-based architecture. And then we will talk about their limitations and how we can solve these limitations with some deeper conversational AI solutions. This is a brief history of neuro conversational AI research. Starting from 2015 to 2016, the first papers on neuro conversational AI appeared with sequence-to-sequence generative dialogue models for simple chit-chat at the time. Then in 2016, Jiwei Li, Vivian and all proposed persona-based conversational model to make the chit-chat model more consistent. At the same time, people started to explore task-oriented dialogue in a neural setting with the retrieval approach or optimize the dialogue policy in end-to-end pipeline setting. More recent work in 2019, like Transfer, and Hello GPT-2, use a pre-trained language model for personalized and task-oriented dialogue models. So let's see the architecture of a very basic vanilla sec-to-sec conversational AI system. So this is a simple 4-step recipe. You use the data from human to human conversations, and then you choose a sec-to-sec model. Today, we mostly prefer using large-scale pre-trained language models. And step 3, we train the model with supervised learning and finally evaluate the model with either automatic metrics or human evaluations. We will go into details in the next slides. Let's start with the data set. On the left-hand side is an example of 2 humans talking to each other. So there are many other kind of human-to-human conversation databases. Here's a list of them. These data sets are pre-processed to have only 2 speakers, usually no more than 2 turns. Now, for vanilla sec-to-sec system, there are 2 families of generative models. One is the upper part of the slide showing an encoder-decoder architecture, where the dialogue history goes into encoder and the response comes from the decoder. Second is the causal decoder architecture, where both the dialogue history and response are input similar to a language model. Let's zoom in on these 2 parts and describe how the decoder is trained. In general, we use maximum likelihood estimation in supervised learning. Independently of which architecture, the model is trained using the golden response provided in the dataset. The output of model is a probability distribution over a vocabulary. If we use greedy decoding, the model will output a token with the highest probability. So the model is trained to maximize probability of the target sequence tokens. Right? And we use a log probability. This becomes a loss for the model, which is cross entropy loss. After the model is trained, we're going to use it to generate responses. Here we use greedy decoding. We started decoding by providing to the model the start of string token. The model then generates a distribution over the vocabulary. And then we choose the token with the maximum probability. This is the greedy step. The output will be a token here, how, in the example. We repeat this until the model generates the end of string token. Notice here we are describing the decoding process. The model can be both an encoder, decoder, or decoder-only architecture. This is to tell you that the decoder process is model agnostic. There are many automatic evaluation matrices that compare the machine-generated responses with human responses. Perplexity shows how likely the model is to generate the goal response. N-gram overlapping gives you the blue score. And distinct n-grams also measures how many unique n-grams in the generated responses are. Higher the distinct n-grams means the higher diversity. Right. However, these scores cannot accurately measure the quality of generated responses, so sometimes human evaluation is also necessary. So one of the popular human rating system is called Likert. Dialogue history and model response are shown to human judges, and the judge is asked to give ratings, usually from 0 to 5, according to the following 3 different aspects. Humanness, where the judge decides whether this response sounds human-like. Fluency, how fluent the response is in terms of grammar. Coherence, where we decide if the provided response is consistent with a given dialogue history, also known as discourse. Moreover, we can do the same human evaluation in a dynamic fashion, where the judge herself interacts directly with the system. The judge interacts with the system, who also judges and gives a rating from 0 to 5 of the system response according to the 3 aspects we mentioned before. Another evaluation method is A/B tests. So the human judge here looks at the output of 2 systems, system A, system B, and one of the system could be, of course, a human as a Wizard of Oz setting. Then the judge judges the system in comparison, and the judge is asked to choose between system A and system B according to humanness, fluency, and coherence. Once again, we can have a dynamic A/B test where the judge is asked to interact directly with both systems A and system B and rate or choose one of the 2 systems according to the 3 criteria again. So here, the judge also needs to provide a justification about why they choose one system over the other. This paper shows that this dynamic A/B testing gives a better statistically significant results than the static human evaluation. Now we are also going to introduce the many limitations to these vanilla side-to-side conversational AI. So the first limitation is a lack of diversity. Here we have this conversation between system and the human. Human, what are you doing today? System, I don't know. Human, what is your name? System, I don't know. Human, what is your favorite food? System, I don't know. So we can see that this kind of vanilla side-to-side setting trained with MLE laws will generate repetitive responses because it falls into a local minimum and always generates high frequency response from the training set, such as I don't know. It is too weak in terms of parameterization. It does not have enough capacity to capture the one-to-many relation between dialogue context and responses. We will see how to solve this problem later on. Another limitation is the lack of consistency. Human, where were you born? System, I was born in Canada. Where are you from? England. You? Where did you grow up? I grew up in Texas. Very inconsistent answers. This is because different speakers in the training data will have different personalities, demographics, and preferences. And the model is trained on large data sets that consist of all these different speakers. So it does not have the mechanism to encode the attribute information. So it just generates inconsistent responses from different speakers. A third limitation is a lack of knowledge. Here, human says, what is the weather like today? System, I don't know, maybe sunny. Human, I'm going out to Taylor Swift's concert today. I hope the weather is good. System, who is Taylor Swift? Human, okay, never mind. So we can clearly see that such a vanilla setting system does not have any capability of interfacing with the outside knowledge base, such as Wikipedia page. So it doesn't have the knowledge and cannot carry out engaging conversation with a human. Another limitation is the lack of empathy. Here, human says, I messed up my project today. System, what is your project? I think I might get fired. Oh, then you need to find another job. No empathy at all. Conversational methods without empathy, it will give user a bad experience because the vanilla model just maps input to output with no capability of recognizing the human emotion and no ability to respond to the human accordingly. A very important limitation to vanilla seg-to-seg model is a lack of controllability. Here, human says, hi, how are you? Model 1 can say, I'm good, thanks. Model 2 can say, I had really a bad day. Model 3, I'm okay, how was your day? Model 4, I'm okay, I just finished my training session in the swimming pool. Which of the answers is good? Our vanilla seg-to-seg model does not have the ability to control for either the response style, the topic, or the engagement. More importantly, sometimes it will even generate inappropriate responses. So we need to have a mechanism of controlling dialogue output. Another important limitation is a lack of versatility. Seg-to-seg models were first invented for open chit-chat, one turn at a time, sometimes at maximum 2 turns, input to output, human to system. Very well. But for task-oriented systems, we have all these modules from natural language understanding, data, dialogue state tracking, dialogue policy learning to natural language generation. All these modules need to be incorporated into a seg-to-seg architecture. And we also need to access the external knowledge base, as you have seen before, to answer questions and user queries. How can we do this? How can we include all these modules and the access to the external model into a single generative model? That's a challenge. So in summary, all these limitations to vanilla seg-to-seg systems need to be addressed. So how can we overcome these limitations and move towards a deeper conversational AI? Deeper in terms of architecture, but also, very importantly, deeper in terms of a conversation with the user. So the first limitation is that it gives boring and repetitive answers. So Zhao Jianling will now talk about how the solution.
So there are many existing solutions for diversifying dialogue response, including the first training and decoding strategy, such as maximum mutual information objective function. Instead of only maximizing the probability of target response T given dialogue context X, MMI join maximizing the probability of T given S and S given T. In the decoding time in practice, the model first sample and best sequence according to the probability of T given S, then re-rank the response with the probability of S given T. In terms of model architecture, conditional variational autoencoder is a good solution. Given a dialog context S, CVAE first sample the latent variable Z according to dialog context S, then generate a response by conditioning the dialog context and the latent variable. The third solution is more data and large model. For example, large-scale pre-training. And the fourth is decoding strategies such as top K and nuclear sampling. We will discuss in the next 4 slides how to use pre-trained language model and leverage better sampling strategy to generate a diverse and coherent response. The vanilla sec-to-sec trained on very small conversational corpus are not very efficient, and they overfit easily, and generate response is not often repetitive and not very grammatical. Solution for this is to pre-train the model first, then use it as a initialization for the task. There are different pre-train strategies. The first is pre-training on a large-scale web text, such as Common Crawl. For example, BART and T5. BART is pre-trained by the autoencoder loss, that is random masking some input tokens, then reconstruct the original input with the decoder. T5 also random masks some input tokens, then predict the missing token by using the decoder. The second is pre-training on the conversational data, such as public social media conversations. So Mina and Blender bots are pre-trained on the massive conversational data. Language mods such as GPT is a good initialization for causal decoder. GPT and Dialog GPT are both unidirectional language models that pre-trained in an autoregressive way. But one pre-trained in a general text and the other pre-trained with a massive dialog data. Bing search and greedy search decoding strategy often produce repetitive response in open domain conversation. The plot from this paper by the team from Washington University showed that contrary to text generated by Bing search, humans generate more surprising text with fluctuating probability. They thereby propose nuclear sampling by sampling the candidate words from the top-end ranked words, whose accumulative probability is above the threshold P. To give a more clear picture of top-end ranked candidate words, we showed a picture here from Hunky Face. If we set P equal to 0.9 in the first step on the left-hand side, the top-end candidate will be the first 9 words, whose accumulative probability is 0.94. In the second step on the right-hand side, the top-end words are the first 3 words, whose accumulative probability is equal to 0.97. At each time step, the model sample 1 token from the top-end candidate's word to generate a response. In general, this decoding method generates more diverse and interesting response compared to greedy decoding and the Bing search.
The second limitation of vanilla sec-to-sec setting is the lack of consistency. Different speakers in the training data have different personalities. These are all speaker attributes.
Personalizing chatbot is therefore a strategy to improve the consistency of a dialogue model. This can be done in multiple ways. For instance, by learning speaker embeddings, which is a feature vector that represents the speaker with its attributes, or by providing a personal description as part of the input of the dialogue model. In both cases, specific datasets are needed for the task. These datasets include persona attributes, for example, like name, addresses, preference, and so on. In the next slides, we are going to give a little bit more detail about these kind of datasets. So here is an example of a dataset used for personalizing a conversational agent. The personal information from human 2 are, I like to ski and I'm 25 years old. Then the dialogue begins by a human saying, human 1, hi, what do you do in your free time? And human 2, I enjoy going to the mountain and skiing. And then the human 1 again, that's cool, you should be young and strong for this activity. And human 2, oh yeah, I'm 25. As you can see, the human 2 recalled the information from the personal description. I enjoy going to the mountain and ski and so on. Indeed, this dataset has been specifically collected for this kind of task by pairing two annotators and asking them to follow a certain persona description. The two annotators are instructed to talk each other, and if one of the annotators asks about personal information, it requires following the persona assigned. This dataset can be used to train conversational models that generate a consistent response by providing the personal description as part of the input. In the next slides, we are going to see one instance of a model that leverages this kind of dataset. And on the right-hand side of these slides, we show similar datasets that follow the same structure. In this slide, we describe a personalized dialogue agent. One promising way to approach personalized dialogue agent modeling is via transfer learning. This particular work, called Transfer, uses a pre-trained language model, GPT-2 in this instance, and fine-tune it into a personalizing dataset previously described. From the picture, we can see that the personal information, the dialogue history, and the response are formulated as a single sequence. The model is trained to generate the system response by conditioning on the persona and the dialogue history. And the segment embedding is used to inform the model of which part of the input belongs to the persona description and which to the dialogue history or the response. Blue for the personal information, pink for the history, and green in the response in the image. Then the resulting model is then able to respond on different persona, which means given a dialogue history and a certain persona, the model will reflect the persona provided. Other than explicitly persona description as input to the model, a speaker model uses the speaker embedding to implicitly encode the persona information. This model is trained on Twitter persona dataset, which consists of a set of conversations from 74,000 users. Each user in the dataset has a unique speaker embedding, which encodes the persona information. These embeddings are then concatenated with the word embedding as input to the decoder during training and inference, so to reflect the chosen persona information.
One of the biggest challenges with vanilla models is a lack of knowledge. There are 4 kinds of knowledge in general: textual knowledge from Wikipedia, news sources, etc. Graph knowledge from knowledge graphs. For example, they will store a relationship between movies and directors, such as Steven Spielberg is a director of Transformers. Obviously, this Transformer is not attention is all you need. The third one is tabular knowledge. And then we also have service API interactions, because dialogue systems need to generate API query to access external knowledge. And they need to incorporate the returns from these APIs into the response. So, 早讲.
So let's start with the textual knowledge. Textual knowledge are used to guide the response with the factual information from from Wikipedia. In the existing dataset like Wizard of Wikipedia, the relevant Wikipedia knowledge are provided at every turn. Here we give a dialogue example. A human is chatting with a wizard. Human, my favorite color is blue. Wizard, same, blue is one of the 3 primary colors. Human, I'm trying to recall, where does blue fall on the spectrum of the visible light? Wizard, it's right between violet and green. Here, the wizard responds to the human based on the textual knowledge highlighted in the gray. Therefore, Such dataset can be used to train the knowledge ground response generation model. On the right-hand side, we provide a short list of dataset that contains dialogues aligned with the knowledge. Some of them provided at turn level, some of them provided at dialogue level. Now let's talk about the modeling part. The general schema for including textual knowledge is the following. First, the model needs to retrieve the context-relevant knowledge from Wikipedia. Then, retrieved knowledge is used as the input together with the dialogue history. Finally, the model learns to generate a knowledge-grounded response using the previous described dataset. There are two different ways for knowledge retrieval. The first is use information retrieval system like TF-IDF or BM25. The second is neural retriever, like dense passage retriever, DPR. We can also combine these two methods, like use TF-IDF to first retrieve the candidate documents, then use a neural reranker to retrieve the most relevant information from the candidate pool. Here we give an example. Step 1 to step 4 show the following flow. First, the model used TF-IDF to retrieve the context-relevant information. For example, they retrieved 100 documents from the Wikipedia. Then the transformer encoder encodes each of the document and the dialogue context independently. Then we compute the attention score over the documents. Notice that we have the supervision of the attention because the correct document is provided by the dataset. Finally, the context representation is used by the decoder to generate a response. Other than textual knowledge, some knowledge are constructed in the graph format. To leverage this knowledge, the model needs to learn to retrieve the knowledge from the graph according to the dialogue context and incorporate it for response generation. On the left-hand side, we show an example from Open Dialogue KG dataset. During the conversation, one speaker is asking for a recommendation about a classic book. And the other speaker responds by utilizing the information from the graph. For example, according to user's requirement, she wants the book about American literature and in the third-person narrative. And model needs to reason over the graph in order to recommend the correct book. On the right-hand side, we also show more conversational datasets grounding on the graph. People who are interested in this topic can check this link for more information. For the modeling part, to utilize the knowledge graph information, model needs to first use the dialogue history as a query to retrieve a relevant subgraph. Then encode the dialogue history and graph, and finally decode a response. Here, the knowledge graph is in a triple format. So each triple contains two entities and their relations. There are different ways to implement a subgraph retriever. The most efficient way, the most simple way is to starting with the entity in the dialogue history. Then take all the first order neighbor triples as a model input. But in this way, we could also input a redundant information. A viable way is to train a neural graph retriever that do multi-hop reasoning over the graph and only retrieve the useful information as the model input. Here we give an example of subgraph retriever. This model is namely dialogue KG worker. The model performs multi-hop reasoning over the graph to retrieve the correct entity for recommendation. The model first uses all entities in the dialogue as the initial node. Then the dialogue history and entity nodes are encoded by LSTM encoders, as shown on the left-hand side. Then the graph decoder predicts the relation of the nodes, and the relation receive the highest attention score will be included in the generated graph path. And when the decoder arrives at the last node, it will predict start token. After this, we incorporate a retrieve triples for response generation. Similar to graphs, tabular knowledge are another kind of structured information that is very useful for generative conversational model. This kind of knowledge are actually useful for task-oriented dialogue systems. In the scenario of car assistance, model needs to read the driver's agenda to answer driver's questions. So in the example, on the left-hand side, the driver asks, when is her next swimming activity? Then from the table, we can see that it's on 11th at 3 p.m. So the model needs to read such information to reply the question of the driver. We also list some relevant data set on the right-hand side for more reference. Many papers has been proposed for incorporate tabular knowledge into dialogue models. The basic idea is to convert the tabular knowledge into triples, similar to the graph. Then the knowledge triples are used as the input to the model together with the dialogue context. There are different ways to do this. The first is key value retrieval network, KVR, based on the sequence-to-sequence model with attention over triples. Man2Sec instead perform multi-hop attention over the knowledge base and use the pointer network to copy the correct entity from the input. Neural assistant encode triples and history separately. Then decoder fills the information and decoder response. In the scenario of task-oriented dialogue, systems usually need to query the external API to complete the user request, like restaurant booking. In such scenario, the model not only needs to generate a response, but also needs to generate API call according to user provided information. In the example, user wants to book a table for 6 people in an expensive restaurant with British food. Then model needs to generate the API call according to this information. Then model get the API return and display the information to the user, and adjust the API call according to user preference until the user confirms a reservation. On the right-hand side, there are many datasets provide such annotation for building both modularized and end-to-end task-oriented dialogue. But in this section, we will focus on more in the end-to-end setting. Here, we talk about how do we build such end-to-end system that is able to interact with the user and external API at the same time. First of all, give a dialogue history. Model generate an API query, which contains the information about a user request. In the example, user want to book a cheap restaurant. The model first generates query for search the cheap restaurant. Then the return API result shows that there are around 1,000 cheap restaurants. And this query result is used as the input to the model. And then model needs to recommend the options to the user or ask for more information if there are too many options. Once user confirms her booking, system needs to issue the API, booking API. If the booking is successful, the model replies with the reference number. If the booking is failed, for example, there are no such restaurant or it has been fully booked, then the model needs to ask user to change her requirement. So there are many instantiations under such framework. The first three examples, GPT neural pipeline, simple DOD, Soloist, are based on pre-trained language model GPT-2. The main idea of this work are format API query response using a single autoregressive language model. During the training, they first concatenate dialog history, API query, API result, and a response into a single sequence. Then train the sequence as a language modeling task. During the test time, the model first encodes the dialog history, then generate the API query, and after that, encode the API query result, and finally decode the response in the autoregressive manner. One instantiation used encoder-decoder architecture are Sequencity, DAMD, and MinTL. They represent the dialog history as the concatenation of the previous dialog state and current user utterance. Then the dialog history is used as the input to the encoder, and a decoder decodes the API query. Then the API query result is encoded as an embedding and incorporated into the initial state of the response decoder. And finally, the response decoder decodes the response.
The fourth limitation of vanilla sect-to-sect is a lack of empathy in the system. There are two lines of work that focus on empathetic dialogues. The first one generates the emotional response according to a given emotion. Works such as Mojitalk, emotional chatting machine, they assume the generation is conditioned on the given emotional input. But we often do not know which emotion is appropriate for generating an empathetic response. The second line of work is to jointly learn the user emotion recognition and corresponding empathetic response together from data. That includes our work in MOO and CareAbout. So to be empathetic, the model needs to understand the feelings of the conversational partner and reply accordingly. For example, when the speaker said that their son got promoted, instead of asking why, the model should also say congratulations. So here, empathetic dialogue is a good data set. This is a good data set for modeling empathy. Here, we can see that the data set provides a situation where the speaker currently is facing and the emotional label of the speaker. The listener needs to understand the speaker's emotion and reply accordingly. One common way for modeling empathy is learning emotion recognition and response generation jointly. Here, MOO by our team first captures the user emotion and output an emotion distribution, right? Based on this, MOO will softly combine the output states of the appropriate listeners, which each is optimized to react to certain emotions. And then MOO will generate an empathetic response. This way, MOO will select the most correct listener according to the user emotion to make the appropriate response. Emo prepend uses pre-trained emotional classifier to find the user emotion, and then use this emotional label predicted as additional input to the model and generates a response. CareBot, also by our team, uses a very different approach. It uses a fine-tuning method of the GPT pre-trained language model on a particular empathetic dialogue data set with 3 learning objectives, namely emotion detection, as a pseudo-tags, response generation, and sentence selection for the response. The fifth limitation of vanilla sect-to-sect model is a lack of controllability. Large conversational language models such as Dialog GPT, Mina, BlenderBot are very good at conducting conversations with humans. One of the main problems of these models is its lack of control over response style, topics, repetition, engagement, and so on. So being able to control the response will be very important so that the response is not random and it will be more engaging and more reliable. So for example, sometimes we want the system to proactively ask questions to the user that's of interest to the user. And very importantly, we don't want the system to generate inappropriate or even toxic responses. Andrea.
To solve the lack of controllability problem, we are going to describe 4 approach/solutions, namely, the first, low-level attribute control via conditional training and weight decoding. Second, fine-tuning on a specific style dataset. Third, model perturbation control by using plug-and-play language model and residual adapters. And number 4, control it by conditional generation. Actually, this is even more. They compare 3 different methods, retrieve and define, PPLM again, and CTRL. Now we are going to describe these approaches in more details. Let's start with the first one. What makes a good conversation is one of the first work that tries to control low-level attributes from a conversational model. In this paper, the authors examine 2 controllable text generation methods: conditional training, by conditioning the decoder with a control variable at each time step, and weight decoding, which reweight the output distribution of each token based on a scoring function. To control 4 actually important attributes of the chit-chat dialogue, which are repetition, specificity, response relatedness, and question asking, as we can see in green in the picture in the slides. They pre-train a conversational model on over 2.5 million Twitter message response pairs and fine-tune it on a persona chat dataset using conditional training, and they manually define the weight decoding function for each of the attributes. Again, this 4 shown in the picture. This paper conducted a large-scale human evaluation, and the main finding of the paper is that the controlling low-level attributes, repetition, specificity, and so on, the resulting dialogue agent is more engaging and sound more like a human. So it improves the overall dialogue quality. Another way to make conversational models more controllable is to fine-tune them with a special kind of loss function. In this paper that we show in the slides, Style DGPT, the author proposes a KL loss and a style classifier as a fine-tuning step to steer the response generation toward the target style on both word level and sentence level. They use an existing conversational model, for instance, Dialog GPT, which is already good at making conversation, and they fine-tune it with 3 pieces of loss function. The first 2 is non-conversational target style text, both at word level and a sentence level, as we can see in the equation L of W and L of S. And they further fine-tune the model with conversational data together to avoid forgetting how to generate conversational response. And this is shown in the equation as L and NLL. In this way, they can inject the target style into a conversational model. So far, this has been done using 2 stylistic data, archive papers, so more scientific style, and Holmes' book, which are more crime fiction style. The results are good, but to be noted, an entire model is needed for each style, and thus is not actually really plug and play and controllable in many different directions at the same time. So now we move on to another model that controls conversational model using plug and play methods. This paper we are shown here is also from our group, and it's called Plug and Play Conversational Models. This uses PPLM, also known as plug and play language model, as an approach for controllable language, which is an approach for controllable language generation, for controlling the style and the topic of the responses of a large pre-trained dialogue model, which for instance is again Dialog GPT. This method does not require any dialogue-specific dataset and does not rely on fine-tuning. PPLM, however, is well known to be compositionally very expensive at the coding time, and thus is not very suitable for conversational model. Thus, we propose to first generate style topic consistent responses using PPLM, and then using this generated response to optimize residual adapters for directly learn how to steer the original model toward a certain selected attribute. In this way, the model is going to be very efficient at decoding time, thus suitable for conversational systems, and show actually a very high level of control over 3 styles and 3 topics, while being very fluent. You can see in the slide an example of responses generated by our model. Finally, we are gonna show the 4th approach and paper that tries to approach controllable response generation. In this paper, calling Controlling Style in Generated Dialogue, the authors compare 3 existing controllable generation methods in open domain dialogue on about 200 different styles. They compare the retrieve and redefine, which is use a retrieval model to get meaningful dialogue responses and use another model to convert the response to the desired style. They compare PPLM, like we have seen in the previous slides, and they compare CTRL, which trains a model with control codes as the first token of the dialogue history. This allows to condition the response generation to different styles by just changing this control code. Retrieve and redefine and control needs to have a label training set, a label training data that connect responses with the corresponding style. And instead, PPLM requires a discriminator. Since there is no dataset out there with 200 different styles, the author proposed to generate style label for 4 existing datasets by training a style classifier on image chat dataset, which is annotated with 200 different styles. The main take-home message from this paper is the following. Retrieve and redefine is actually not very good in style control generation. PPLM style do not perform very well when you have a large set of style, like 200, and an inference time is a bit slow. And that conditional language generation approach is convincingly generating controllable language responses.
The last limitation we're going to cover today is the lack of versatility of this vanilla sec-to-sec models in deep conversational AI. Sec-to-sec, as I mentioned before, was invented for chit-chat systems with a single turn. However, human conversations weave between chit-chat to task-oriented conversations. So we do need a single model for both purposes and perhaps more. During the tutorial, we have seen multiple ways of incorporating knowledge into a dialogue system. We have also seen a generative model for task-oriented dialogue that issues APIs, queries a knowledge base, and then uses the return to generate proper response. An important intuition here is that these models shown in the slides together share a similar interface, right? The input and output with different instances.
Based on this intuition, a single model can be trained to encode all sorts of dialogue skills. For instance, all the data sets we presented so far can be used to train a shared dialogue model with different dialogue pairs. For example, as we can see from this image, we can connect with the dialogue model the history to a response, the history to an API query, the history plus a knowledge base, which can be a table, which can be a graph, which can be a text, to a certain response. And we can also do like from dialogue history to an emotional model to a certain response. The resulting system will not be just chit-chat or task-oriented, but we'll have a unique dialogue model that responds to human input, any kind. So for example, we can see in this instance that we show an example, we have both in the first turn, a task-oriented turn, what was the weather like today, where we have like information from an API call. Then in the second turn, we have knowledge from a knowledge graph, and then we have no knowledge. And so we have a more chit-chat response. For example, haha, you know a lot. And the model responds, I try my best to be helpful, which is purely chit-chat and is englobated into the flow of the conversation. The only problem here will be to understand when and how to use this different dialogue skill. And so in the coming slide, we will see how to build such a model, and we describe datasets specific for this kind of task. Let's start with datasets. Several datasets have been proposed for blending multiple dialogue skills, for example, persona chat, Wizard of Wikipedia, or chit-chat and task-oriented into the same model. The first was the Dodecathlon, which is a collection of 12 datasets. The second is a dataset that connects the flow of multiple datasets, such as persona chat, Wizard of Wikipedia, and empathetic dialogues. The third, which is actually very new, adds a chit-chat turn to well-known task-oriented dialogue datasets, such as schema-guided dataset and multi-WAS. Now we are going to describe in more details two models for mixing chit-chat and task-oriented dialogue system. This is one of our work from our lab, which actually is called attention over parameter. In this model, each dialogue skills is encoded with a set of specific parameters for these instant transformer decoders. Once the model learns each of the domain skills independently, then we train a composer model that learns how to select and mix the multiple decoders. This allows controlling which skill has to be triggered given a certain dialogue history. To give a more concrete example, if the model needs to generate a booking API under the hotel domain, then the composer will mix the hotel decoder with the booking API decoder and mix them and generate the correct system response or API call. For mixing multiple decoder, we propose two options: attention over representation, also known as mixer of experts, and attention over parameters. Let's see this in more detail. So the paper proposed these ways. On the left, we have a very vanilla way to decode where we give a dialogue history in input and we generate a response. In the middle, we see attention over representation, or also known again as a mixer of expert, which forward each decoder, gets the embedded representation in input from each decoder, and mix them based on the attention score computed by the composer. Then finally, we have the third option on the right, which is called attention over parameters, which instead of multiple forwarding, we mix the parameter all together at the first, and then we plug this parameter to a decoder to make a single forward. We have a corollary in the paper where it shows the how P is more computationally effective than OR. Interested reader can refer to the original paper. Now we move on to the second kind of model that we use for mixing both chit-chat and task-oriented. Similar to attention over parameter, the adapter bot, which is the model we are going to present right now, combine multiple dialogue skills into a single versatile conversational model. The adapter bot uses a fixed backbone conversational model such as Dialog GPT, showed in gray in the figure. Then it learns each dialogue skill using independently trained residual adapters, also shown in the figure as adapter layers, where the POSE, which is actually stands for positive responses, is actually highlighted. Depending on the skills, the model can process multiple knowledge types, such as text, table, and graphs, and is shown in red in the slide. Finally, a skill manager, which is a BERT model, is trained to select the most appropriate adapter and thus the most appropriate dialogue skill based on the current dialogue history. Also, this is shown in yellow and in gray to the right of the image. So, as previously mentioned in the slides, these dialogue skills are triggered automatically via a skill manager, and thus allowing high-level control over the generated responses. The adapter bot has 12 response styles taken from plug-and-play conversational model that we have seen a few slides up before. And it has 8 goal-oriented skills, from weather information to movie recommendation to Wikipedia grounded conversation. The adapter bot provides also personalized and empathetic responses. So, to summarize, there are different ways to combine dialogue skill into a single versatile conversational model. We have seen 2 of them in detail, namely attention over parameter, which model each dialogue skill separately, both chit-chat and task-oriented, and learn a composer to select the skill and the response accordingly. And we have seen more in detail adapter bot, which fine-tune an adapter per each skill and uses a BERT model as a composer. We also would like to mention the blender bot, which falls, in our opinion, under this category, since it multitask learn multiple dialogue skills into a single model.
Despite the hard work, challenges remain for generation-based conversational AI systems. Here are some of them. We must continue to address the challenge of reinforcement learning self-chat. Learning directly from conversing with a human is a grand challenge for conversational models. Even the most powerful language model cannot learn directly from human interaction. These 3 papers here showed us how to learn directly from human interactions by learning a reward signal directly from human responses and transforming it into a meaningful update for the model. However, challenges remain, as these are only toy data sets, and scaling to new domains could be very, very difficult still. Collecting data set is a very costly process for both task-oriented and chit-chat conversational AI. Designing models that are less data intensive is crucial for the future of development of conversational AI systems. The 2 approaches that are very important are zero-shot and few-shot learning. So far, a few works have been proposed to do this, and the performance of a few-shot learning model is still far from perfect. Few-shot learning means, how do we learn to converse in a new domain by learning from another domain? Here is an example of a schema-guided dialogue dataset. It has textual description for zero-shot news services, slots, or intent. But there is no training data for this domain. We need to learn from another domain and adapt to this. So far, the most effective way for few-shot learning is to use pre-trained language models and fine-tune them with a few examples. For task-oriented tasks, there are some models that are pre-trained with dialogue data. For example, Todd, Bird, SC, GPT, and so on. However, we hope to have either better pre-trained models or better few-shot learning strategies, such as those we describe in the next slide. As an example, another way to implement few-shot dialogue system learning is to apply meta-learning. The goal is to train a model on a variety of learning tasks, such that it can solve new learning tasks using only a small number of training samples. The general idea of using model-agnostic meta-learning in task-oriented dialogue is to learn a domain-agnostic dialogue system, which can be quickly fine-tuned on new domains. Similarly, for task-oriented area, our team previously applied MAML to quickly adapt to a new persona style without persona description, just by using previous dialogue by the same users. Large language models such as GPT-2 or GPT-3 can be considered meta-learners for task-oriented dialogue systems. Instead of fine-tuning a model on some data, here in the left figure, we leveraged the power of language models for few-shot learning by just providing the right prefixes, such as here in the middle figure. This is an interesting direction because there is no training involved. We just prime the language model with the right, correct prefix. Similarly, we can use GPT-2 or GPT-3 to quickly create a chit-chat conversation system just by providing an example of a conversation in the context, and it can generate human-like response automatically. However, this kind of model is still very large. It requires multiple GPUs once it is being deployed. There's no mechanism, even in GPT-3, to explicitly control for knowledge. It is also not accessible to the research community. Lifelong learning in dialogue system is a relatively unexplored area. It usually refers to the user speaks with the system, and the system becomes more knowledgeable by interacting with the user. This requires a way to extract attribute from the previous conversation and being able to remember it and use it without forgetting anything previously. This is a preliminary work to extract user attributes, and it is still challenging as to how to use it properly. For example, here, human talks about kids to the system, and a few days later, the system should be able to query the user about their kids. Another way of continual learning in dialogue system is to add new domain or dialogue skills to existing model without forgetting previously learned one. For example, here, the system learns new knowledge skills sequentially by first adding slot to NLU DST, secondly, adding new domains, and then adding new dialogue skills without retraining with all the data. This is still an open and understudy problem. Generative conversational models that were trained on internet social media data might generate inappropriate responses. Here are some examples from misleading response to toxic response to gender bias and so on. Here are the responses outright sexist. It is very important to mitigate these inappropriate responses to avoid harmful and unsafe consequences. The first step towards building a safe generative conversational model is to filter out the inappropriate response during data pre-processing stage. You can train different classifiers to detect toxic and biased content and get rid of them from the database. Or after the model has been trained, we can also block the engram from the predefined sensitive word list during beam search decoding. This is kind of like self-censoring. The model can still, however, generate inappropriate responses. Even after censoring and blocking, the model can generate inappropriate responses composed entirely of safe words. So what can we do about that? That's a challenge. So for example, we can add another safety layer, such as classifiers for toxic, bias, unethical content, and try to filter, do a post filtering after the generated response. So from pre-filtering to blocking, censoring to post-filtering by safe layers, are there other ways to mitigate inappropriate responses? Can we debias and detoxify model themselves? That's the future direction. Multimodal. Ideally, conversational systems should be able to both talk, able to see. Like humans, it should be able to also learn in a multimodal setting. Here we give an example from image chat where speaker A and speaker B are talking to each other by looking at an image. On the right-hand side, we show a list of databases for multimodal conversational agent learning. This is still a very new area in conversational AI. Evaluation. As we have seen before, having a general and automatic way to evaluate dialogue system is crucial, but it still is a remaining challenge for the most part. Engram-based evaluation metrics fails to capture the semantic meaning of the responses. For example, here, right, speaker A talking to speaker B, where the system response doesn't really capture the meaning of the intention of the user. Turn level evaluation cannot capture repetition and inconsistencies between turns. I would also like to point out the curious case of perplexity. A paper has shown that perplexity has found to positively correlate with interactive human judgments. Looking at this figure on the top side of the slide, the x-axis is the perplexity and the y-axis is the interactive human evaluation score. The paper showed that the lower the perplexity, the higher human evaluation score. There's a positive correlation. Mina is very close to human score, for example. This is actually very neat because perplexity becomes a measure of confidence over the generated response. On the other hand, some follow-up work showed that if the perplexity is too low, the curve goes down. The human evaluation score decreases. So it's not clear still. In general, learning a good evaluation model is as hard as learning the dialogue system itself. It's a chicken and egg problem. It's still unclear how general the scoring model and metric are, and if we have a perfect evaluation metric, we should be able to have a perfect response scorer and leading to a perfect conversational AI system. So this is an open and important problem. Finally, we'll give you a list of current conversational AI shared tasks and challenges. These are mostly task-oriented dialogue challenges in dialogue system technology challenge. And there are other new challenges that includes both task-oriented and conversational chit-chat. These challenges are a good resource for data sets. This is a list of all data sets we have mentioned in part 2 and also part 3 of this tutorial. You can click through them and find these data sets for your experiments. In summary, for all these challenges, remaining challenges, we have future work that needs to be done. We need to put human in the loop for reinforcement learning and self-chat. We need better strategy for few-shot and zero-shot learning. We need to have lifelong learning with user experience. We want to mitigate inappropriate responses better on the model itself. Multimodal is still a grand challenge, and we want better automatic evaluations and more shared tasks and data sets. So this concludes our tutorial today. Thank you so much for attending our tutorial today. Everybody, please stay safe.
Bye-bye. Bye-bye.
Hello. Yeah, thank you. Yes. Hi, everyone. So here we can answer your questions, if any. Sorry that we cannot see you live, but please don't hesitate to ask questions. Dario's there. You can talk, raise your hand, and you can either talk or you can type in the Q&A. Of course, it's more interactive if you talk. We'll try to answer your questions. Let's see. Do you know how to raise your hand? You go to your participants and then just click. Or you can also type your questions.
In the Rocket chat.
Better here in Zoom, but you can also, of course, type in the Rocket chat. Could you please share the Zoom link?
Sure.
Okay. Q&A. How do you measure perplexity in different tasks? For example, how perplexity in generating creative text differs from perplexity in empathetic conversation. You want to answer that?
Sure, I can try. Hi. Yes. So I would say maybe it depends by which language model you're currently using. Yeah, because you have the mic on. Sorry, a second. Yeah.
I already muted.
Yeah, but yeah. Sorry, yes. So yeah. So indeed, like perplexity, as you can see in the last slides, we were mentioning that perplexity has shown correlation between human evaluator and there is a correlation between the human evaluation and the perplexity itself. This is actually true and not true, as we also see in that likelihood hub. Yeah. Probably in creative tests, the perplexity is not going to be very good because there will going to be an up and down in terms of high perplexity, low perplexity token, like they show in that top P sampling paper, nucleus sampling, that we also mentioned in the slides around in the middle. I don't know if you remember the first part. And in general, for empathetic conversation, I don't know, actually, to be honest, what would be the correlation.
So I guess your question is that how do you measure perplexity? You measure perplexity of any text the same way. So in the empathetic conversation, you measure the perplexity of the response from the system, right? And in creative text, you measure perplexity of the text generated. So anything that's generated, that's what you measure perplexity on. Okay. Any other question? I have been, very common. You haven't mentioned in the challenges slides the approach to different languages besides English. Do you think that multi-language models are enough to cover current results or practical results? Need specific efforts in any language for which you want to implement a solution? That's a very good question. In fact, this is a general NLP question. It's not just conversational AI. So indeed, in many, today in NLP in general, we have more data in these rich resource languages such as English and Chinese because there's more usage of conversational AI, more user in those languages. But today, actually, we have multilingual language, pre-trained multilingual language models, and also multilingual embeddings we can use for other languages other than English. And indeed, for some languages where you don't have enough training data, the results might not be ideal. And there's research going on in leveraging rich resource language and to try to do transfer learning or zero-shot learning, not zero-shot, but few-shot learning. If you have a language where you do not have enough data, for example, you can check the pre-trained language models available, whether they include your language or not. If they include your language, you're probably in a good position. So for the major internet languages like the English, French, Spanish, and so on, even Chinese, standard Chinese, it's pretty good. But other languages, you might not have enough representation in the pre-trained language models or the embeddings. Then you need to look for solutions to do some transfer learning. You want to add?
Yes, there is. I also connect with one question I found in the Rocket chat about which is the best multilingual pre-trained model that Pascal just mentioned. I would say multilingual BERT for now seems to work very well, or also XLM. We have a recent paper called X Persona where we try to evaluate multilingual conversational model. I will post it in the Rocket chat if you want to know more about it.
Excellent. And so I'm reading the question in the QA. Is it fair to say that the approach that you're taking is to understand, find the stylistic, emotional, personal context, and then use that information to pick reasonable responses given the input from the user and their dialogue history? I would not say, when you say pick, I'm assuming you're talking about retrieval-based. We're not retrieving any responses from a preset of response. We're doing generation. So the whole presentation is more about generating responses and how we use this kind of context to control the generated response. It's not a retrieval-based. There are people who use retrieval-based methods, but retrieval-based means that you need to have a pre-prepared set of responses already. So there are chatbots such as Xiaoice, which has like 60 million, 70 million users. They have so many answers from humans already that they could use that method. So you could try that. But otherwise, what we talked about today is how to control the generation. Another question. What has been your success in transferring knowledge learning across domains, such as banking, travel, insurance? What are some architecture training tips here? Why don't I let you guys respond?
Unmute. Hey, so in terms of cross-domain transfers, for example, banking, traveling, so this kind of insurance. So for this kind of task, we just mentioned about the schema guide dialog. So the current popular approach for tackle this problem is you provide kind of description for the new domain. For example, in the bank domain, you have a description for what will be the major task for bank domain. For example, I want to transfer money, and in this domain, for example, you might have multiple slots. So how much money you want to transfer? So for example, you have slots amount of money, and also your target account. So for these slots, you may need to have some description, natural language description to describe this kind of slot. So in general, you will have this kind of task description and slot description. So when you need to transfer to the new domain, for example, insurance basically is quite related to the bank domain. You also can have a natural language to describe what's the task about insurance, and probably you also need to, for example, which kind of insurance you want to apply and what's the amount of money, what's the price for this insurance. So basically for each slot and each task, you will provide a description, natural language description to help the model to understand this task. And sorry. So so basically the best way is you can leverage a pre-trained language model to first understand the description, and then, for example, this language model can be GPT and T5. And you can first try out your experiment for example, schema guide dialog. that will be good for the practice.
So I'm gonna allow someone to speak. Dara.
I mean, like this means like you like.
You need to unmute yourself to talk.
No, I mean
Hello?
Hello?
Yeah, can you talk? Dara
Yeah.
Kutecha?
Am I audible? Am I audible?
Oh, I cannot hear.
Yes, you are.
Okay. Okay. So thank you for the great presentation. So one general doubt I had was that how do you incorporate longer dialogue histories in the model, given that there is a limited sequence length that we can use?
Limited sequence. So we would incorporate, I think, up to 5. It's like dialogue contacts. It's what's usually called discourse. So we have experimented with incorporating a dialogue history of 3, windows of 3, turns of 5. I think up to 5 we have tried, right?
Yeah, more or less, yeah.
Yeah. So you obviously you cannot put the whole dialogue history in there. You can. What you want to answer?
Yeah, I would like just to add maybe. I would like just to add on this, like if you are on task oriented, for example, you could try to provide the previous dialogue state as input. And so you just keep 1 turn. But in general, as Pascal say, yeah, we try no more than 5. And this is such an open problem in dialogue also. Like, I don't know if you want to add something, Lynn, but I think it's still an open problem.
Oh, great, thanks.
I saw another question. Is there any? No. I saw another question. Another question on what is the chatbot? Does it add value to have both task-oriented and chit-chat? If you can measure, it's a very good question. If you can measure task-oriented user experience with task completion, how do you measure the user experience of the system with both task-oriented and chit-chat? Okay, so first of all, does it add value? I will imagine the chatbots of the future. Actually, even if today, if you use the virtual assistants like Siri or Alexa, a lot of users would tend to go randomly into task-oriented and chit-chat mode. So you kind of have to handle that. How do you measure that? I would say, for developers, you would record this user data and then you will hand segment them into task-oriented and chit-chat, and then you will use the normal measures for each task, where task-oriented is measured by task completion and chit-chat is measured by how engaging it is with human evaluation. So in the future, perhaps in research, we can come up with better measure. For example, how seamless a system can go between the two will be important. When humans talk to each other, we don't just focus on one. That's one question. Emotion recognition. Can emotion recognition models you mentioned differentiate sarcasm? It's a very good question. So sarcasm recognition is itself a research topic, and you are right. Sarcasm can be detected from pitch and the tone in audio, or it can be detected. So in natural language, sarcasm is usually defined as the contrast between the literal meaning, the literal sentiment, and the intended sentiment. So you can have a sentence that says, "I love working all weekend," and that's a positive sentiment. And the tone will be, "I love working all weekend," will be negative. So there's a contrast, and that's usually what's defined as sarcasm. It is sometimes it's not so easy to detect sarcasm from words only, and it's a different research topic. Do we have sarcasm in conversational AI? Whether we can learn that, it's a very good question. Do we have sarcasm label data? We can probably learn it just as another emotional class. We haven't done that, but it would be worth a try. A question on NLU statefulness. Can you ask live? You can ask any question live. You will raise your hand in the Zoom. Why is GPT-3 so hard to work with for the research community? It's super big. We don't have. Is it really only about ethics issue, or does it have to do with Microsoft? GPT-3 is not from Microsoft. It's from OpenAI. And I believe there's ethical concerns that people might misuse it, and also I believe there's it's huge. It's so huge that in general we can't, unless you have enough resources, you can use it. Anything to add, guys?
I'm a big fan. Yeah, I'm a big fan of GPT-3, and yes, I agree with you. Like, it's very large, and yes, I heard that Microsoft since invest in OpenAI before, so they have some exclusive use. But the problem is too large to run so far, and
then there is ethical concern.
Yeah, absolutely ethical concern around there. So I agree. Yeah.
The question. I will read the question from the chat, and then I'll go to the person who raised the hand. Okay. Are there studies on how to define the line between chit-chat and task-oriented in the real world? I would imagine to be crossed often due to conversational drift, given that there are systems that can capture state for both variants, maybe. Yeah, we already covered this. So, so what real-world system tends to do is it would have an intention classifier, and it would detect whether it's a task-oriented query from the user or it's a chit-chat query. And then it will go into two modes of the system. So you can imagine that two systems, and goes back and forth. Maybe I go to the raised hand. Yeah, please, you can talk. Yes.
Hi.
What's your question?
Yeah, thanks for the talk. My question was.
Oh, I cannot hear. So yeah, now you please say. I couldn't hear you. Can you say your question?
Yeah, thanks for the talk. So my question had two questions. One was particularly on the SLU bit. So there isn't too much work on speech to intent or speech to entity. Some basic work out of Canada. So what has been, because training NLU on text is very different from the erroneous transcripts if you use an ASR and NLU separately. So what has been your experience there, one? My second question was, what has been your experience on end-to-end conversation, even for task-oriented dialogues, versus splitting out an NLU and a conversation system separately? Yeah.
So I talk my experience first, and feel free to add. So first of all, your question was ASR, right? So there will be errors in ASR. Indeed, spoken language conversational AI, as opposed to just typed conversational AI, has been around for a long time. And actually, they are the ones that have been around for 30 years. ASR error has always been an issue. But today, so ASR performance is very good today. So fortunately, so the transcription can be very good today. And the problem downstream is not the transcription is correct or not. It's because when we speak, we tend to repeat and we tend to drop words. There's some kind of artifacts and some non-speech acts. And these are the things that need to be understood by the Convey system. So I guess it depends on what kind of data you use to train. So I think if you can just use ASR output as training to a Convey system, it should be able to handle that. Now, and then you were asking about the comparison between basically slot or modular system and the end-to-end system. So I say my opinion first, and you can add. So modular systems were more or less invented for task-oriented dialogue systems. So you have NLU, you have dialogue management, and then generation. And they're more, you can control them better, you can design your task better. And end-to-end generation-based system, as we covered during the tutorial, they were originally also invented for chit-chat because it was like one turn, chit and chat and chit and chat. So today we are seeing the convergence of the two in a generation-based model. So I guess one is more controllable for task-oriented dialogue task completion, and the other one is more for open chit-chat. So we hope to see that we can use generation-based model for both. Anything to add?
Yeah. So in terms of the error from I still hear that.
So in terms of the error from the ASR, there might be some like entity errors. So in this scenario, probably we need one like a kind of like entity correction. For example, you might need to have like a kind of entity pool to automatically correct those like entity mistake. And for the evaluation for the modularized task-oriented dialogue. So nowadays there are standard metrics to evaluate. For example, in NLU, we have like intent accuracy and slot F1 accuracy for the NLU. We have joint goal accuracy for the dialogue state tracker, and we have the success rate for the policy dialogue policy. But for end-to-end systems, nowadays there is no gold standard for evaluating end-to-end systems. For example, to evaluate the success rate for end-to-end task-oriented dialogue systems, we might need to build a user simulator. But building a very good user simulator is as hard as to build a good dialogue systems. So another way is to perform the human evaluation. Basically, the one human is chatting with the system. So in this case, at the end of the conversation, the model will give the feedback whether the system accomplished the goal of the user. Yeah. Yeah, you want to add something?
I think we covered quite much for. If you want, I don't know if you cover all of you ask several questions. So I think we cover more or less big overview. Yeah, welcome. And you always feel free to ping us in Rocket Chat.
Mm-hmm.
So there's another question on research on the impact of language involvement with respect to lifelong learning, a system that can teach new language words such as topic-related words that the system has not seen before and gain that knowledge for future use. So we did talk about lifelong learning in our tutorial, and then you can add words into the utterances you want to retrain the system with. Do you want to elaborate?
Hi. So in terms of this problem, I think one way to approach this problem is, for example, to learn from the new language words from the conversation. So one way is to build information extractor to extract the attributes from the conversation. For example, the new words. And in the conversation, we may involve some kind of concept of these new words. And one way is to convert it into like a graph representation, and probably there's a way to train the model, for example, to leverage the graph information we extract in the previous conversation and apply to the future cases. So we have done some work for in terms of extract the information from a conversation. But in general, we need to build such data set to teach model how to leverage the extracted information in the graph.
I would like also to add there are two works about this continual learning that are quite interesting. One is from Jason Weston from 3-4 years ago in NeurIPS, where they basically learns reward from a teacher. So learn how to continuously learn new.
Type the reference. No.
Yeah, I will refer you in the Rocket chat later. We also mentioned it in the slides in the continual learning, where basically they try to learn new skill through time by learning directly from a teacher. So you learn to gain reward just by chatting. And also another work from Bing Liu that I will also mention in the Rocket chat, where as it's very similar to what just Lynn mentioned here about growing knowledge in your KB and you reuse it through time. Anyway, both of these are very interesting and very relevant for current and future research in conversational AI. I think we can move on to the next question.
I'm typing the answer to Ahmed on what kind of a where can you start? I'm giving people the, you can start in terms of to learn technology, you can start by this tutorial and the references. You can also go to some online courses on NLP, because the foundation to conversational AI is NLP, fundamentals of NLP. All right, so another question, minimizing the inappropriate responses generated. Is part of the goal of having an unbiased model to have one which is unable to generate responses which could be construed as an opinion of some kind? Further, so I will answer this part first. Of course, the chatbot needs to have an opinion because users will ask for opinion. The inappropriate, so inappropriate doesn't mean having an opinion. Inappropriate responses so far have been defined, including sexist, racist, and toxic answers. So inappropriate languages. So the goal is to mitigate, to prevent this kind of responses. Because as you know, when we have models that are trained from human to human conversation, especially from large pre-trained language models, there can be bias and toxic answers that's learned, and we need to mitigate that. Now, further, should mitigation of this be internal to the model or handled with some classifier which cleans the output? I think we mentioned both. It is ongoing research. It's a very new research direction. How can we mitigate inappropriate responses in conversational AI? I think we mentioned from cleaning up the data before you train it to internal to the model, and to handle with some pre-classifier and post-classifier. So every which way you can think of to mitigate such a response is worth doing. So there are solutions like real-world solutions, like some real-world systems will use like a list of sensor words, and when they detect there's response of this kind, then it won't generate that. I think that was triggered by the infamous case of Microsoft Tay, the chatbot. So other than that, people are working very hard on this research of how we can mitigate bias responses. So it feels like it will be hard to define what is objectively inappropriate. Indeed, I think there's certain things, easy things to agree on, that everybody agrees to that is inappropriate. So swear words or toxic responses, sexist. Even sexist and racist, I think we have some training data we can use for the classifier, but you're right. we don't have a very good definition about what is sexist and what is racist. People don't agree on everything, and therefore we cannot we cannot immediately clean everything. But it is a direction that the general direction people agree on, right? We want to eliminate inappropriate responses, so we can work towards that. And it's a research question as well, how to define that. Thank you for this question. Oh, there's another question. I've got a bit off-topic question. Is there approaches to train a chat bot with particular personality, like providing dialogue with Elon Musk or something like that? I love this question. So that's what we call persona bot, right? In a way. Yeah. So chatbot that has persona. Of course, we want to do that. Whether it's providing dialogue with Elon Musk or something like this. This is what we used to call this like a adaptation to a particular speaker. In the fine-tuning data set, I'm sure we can do that. Has anybody done that? Do you know?
With Trump, maybe, yeah.
With Trump. Very interesting. You could try that. We can provide our code to our system, and then you can try to, right? Do we provide the link to our code?
Some repository, yeah.
Yeah. So we will. How do you give them the repository?
I think so. There are many online repository like try. I think a lot of reports in the paper, so they attach the link.
Okay, so you can use any of these chatbot system that's public accessible, including our own, and then fine tune it. Okay. Did I miss any question?
Yeah, there are 2 questions left.
Why? Which one?
I just make sure I understand.
I think we answered those questions. Which question? Which question? We answered all these questions.
And the new statements?
Yeah.
I think they're
yeah. We answered all these questions. Is there any other question?
Let me check in the...
Oh.
There is this question I posted.
Oh, there's a question of, is there universal intelligence to be used to pre-train? I guess you can call GPT-3 universal intelligence or not, but only in English.
I post something in the chat.
Oh, you post something in the chat? Where?
Yeah.
Where?
This is from Rocket Chat.
Where?
Yeah.
I see. Thanks for the question, Xiaoais. And here's an engineer from Xiaoais. Thank you. My question is regarding creative AI combined with deep conversational AI. If anything can be shared regarding the future direction of creative AI and how conversational AI can enhance creative AI of poetry, of music, of singing, of painting through multi-turn conversation with human being. One issue of general domain conversational AI is regarding the construction of contents. Indeed. So I think in our team recently, we also built a adapter bot with different adapters to have to take care of different skills of poetry. So the conversational AI system should sometimes answer a question with poetry. And they can access music. And do you mean that you want the AI system to sing itself? That would be great. That would be very great. But otherwise, conversational AI systems will access, I don't understand what you mean by painting. Perhaps you're thinking that the system would access painting and describe a painting to the user. That would be great as well. It's a lot of work we can do there. I see a hand raised by Dario. allowed to talk.
Hi, I have a last minute question. Well, first of all, thank you for the presentation. It was very clear and informative. And my question was about common sense, in the sense that if I think about how humans learn, so if I'm trained as a waiter and I have to deliver a very hot soup, I will warn the customer that the soup is hot, but not because I was trained to, not because I was taught that hot is bad for humans, but because I know that, because when I learn to talk, I learn from common ground that the person I have in front of me is similar to me. Instead, a machine learning model tend to treat the human like a black box. So you kind of have to figure out the desires, the needs, predict something that you don't really know. And there are approaches in dialogue system learning, like self-play, where agents can talk to each other, sort of develop this kind of common ground. Do you envision this as useful? Do you see it as a promising way to build this sort of common ground that goes a little bit beyond knowledge, beyond learned reasoning? And so, yeah, how do you encompass the notion of common ground in a dialogue system?
So this is in research what we call common sense and common sense reasoning into conversational AI. It's a research direction and various people work on it. You can use Google Scholars to search for relevant papers, but it is a challenge that we're facing. Nobody has a good answer for. So common ground or common sense? Anything you want to add? Yeah.
No, I agree. Like with you, it's open question.
Yeah. So it's a bit harder than empathy, you know. It's a common sense and common ground.
Especially self-chat would be exponentially larger search space in a sense.
I understand. Thanks.
Thank you for the question. Any other question?
I think Ahmed.
Ahmed, you have another question? Ahmed, you have another question? I think earlier he had a question. We already answered his question.
Okay. I asked him to unmute. Yeah.
It's okay.
No, I'm okay. I'm okay.
You're okay. Okay, fine.
We check rocket chat.
Mm-hmm. I think I just want to add the question earlier about Xiaoai's. You mentioned multi-turn conversation with human being. I think conversation is so that combines multi-turn and also lifelong learning, right? So we want conversational AI systems to learn continuously by talking to a human being. So it's not just we adding knowledge or incorporating any external knowledge, but it should deduce some knowledge and learn from a human being. And indeed, there's one research direction for that purpose as well. Lifelong learning with online learning through conversation with humans.
No, just like me.
Okay. Is there any other question?
Yeah. We have another QA session on Thursday.
We do?
Yeah.
What time? Can you type?
Yeah.
So we have another QA session on Thursday. Can you tell people the time, Andrea?
Yeah. Yeah. 1 second. We are retrieving the exact date for the next QA because we have another QA session for everyone has more any kind of interest and wants us to answer more question. And in general, there is always Rocket Chat. There is a channel for this specific tutorial. So feel free to ping any of us in Rocket Chat if you have any question, I would say. I mean, at least from my side.
I'm checking.
Sorry, we're checking the time for Thursday. Can Thursday at 8 a.m. GMT.
Yeah.
Okay, Thursday 8 a.m. GMT is our next Q&A session. So if there's no, thank you very much, Hendrik, for posting that. So if there's no further questions, maybe we'll conclude today's Q&A session. It is also on the NeurIPS website, yes. Okay. Any other, no other question, then we'll end the session today. And thank you all for your attendance and your questions.
There's something that underlies how things function in the world.
I think it starts with being curious. That's where it starts.
We have particle physicists,
designers,
engineers,
economists,
chemists,
biologists,
ethnomusicologists.
I am in IBM Research because I love the people I work with. I admire the people I work with. They're incredibly good, and because they're so good, I can be good.
And that's the beauty of it.
At Capital One, we combine the power of a machine learning model with a cloud-based multi-region infrastructure so that our customers can stay connected to their money anywhere. Capital One, what's in your wallet?
The unknown is not empty. It's a storm that crashes and consumes, replacing thought with worry. But one thing can calm uncertainty: an answer, uncovered through exploration, teamwork, and innovation. An answer that leads to even more answers. Mayo Clinic, you know where to go.
是人类从未经历的时代。从原子到比特，从物理世界到数字世界，数字化的浪潮正在触达世界的每一个角落。那些你从未想过的可能，正和阿里云一起变成现实。你会发现，人工智能学会了忙农务下车间，农民们不再靠天吃饭，传统制造业被一行行代码激活。科技在默默守护生命的未来。我们用上云勾勒无限可能，宇宙对每一双眼睛都开放，空气回到了记忆中的味道。我们用科技让万物互联，风机点亮世界的每个角落，数据在为你跑腿，城市在替你思考。100年奥运跨入智能时代，这个时代注定成就伟大。科技与思维的碰撞从未如此耀眼。从农田到车间，从海洋到天空，数字激发产业澎湃动能，数字驱动经济蓬勃向上。让我们一起成为数字经济的创造者，驱动数字中国。
There's something that underlies how things function in the world.
I think it starts with being curious. That's where it starts.
We have particle physicists,
designers,
engineers,
economists, chemists,
biologists,
ethnomusicologists.
I am in IBM Research because I love the people I work with. I admire the people I work with. They're incredibly good, and because they're so good, I can be good.
And that's the beauty of it.
At Capital One, we combine the power of a machine learning model with a cloud-based multi-region infrastructure so that our customers can stay connected to their money anywhere. Capital One, what's in your wallet?
The unknown is not empty. It's a storm that crashes and consumes, replacing thought with worry. But one thing can calm uncertainty: an answer, uncovered through exploration, teamwork, and innovation. An answer that leads to even more answers. Mayo Clinic, you know where to go.
Hello, I'm Taco Cohen, and together with Rizi Condor, I'm going to be presenting this tutorial on equivariant networks. So equivariant networks is a very active area of research, so we thought it would be a good time to present this tutorial where we can introduce some of the basic concepts and mathematical ideas, mathematical results, implementation details, as well as convey some of the excitement around applications from computer vision to scientific computing. So in part one, I will give a brief introduction to the concept of equivariance and symmetry, why they are important, explain how one can incorporate those into neural networks. Then I'll cover some examples and applications. Without going into great detail in any of them, I hope to convey the breadth of applications of these ideas. And finally, I'll look at one type of equivariant network, namely equivariant networks based on equivariant convolution, of which the well-known convolutional neural network is a special case. Let's start with an introduction where I'll explain the motivation for building equivariant networks, as well as go into some detail on the basic concepts such as symmetry, representations, groups, and equivariance. So before we begin, let's just look at a concrete example that presumably many of you will be familiar with, namely translation equivariance in conventional planar CNNs, convolutional neural networks. So in such a network, we have the main building block is the convolution layer, conv2D, which takes an image and a filter, or in practice, many filters in a filter bank, and it applies the filter everywhere, i.e. it performs a convolution to produce an output feature map or multiple output feature maps. And as you can see, if you do this, then if the input is undergoing a translation, so will the output feature map. And this simple property is called translation equivariance. So why is that a good idea? Translations are so-called symmetries, at least in many visual learning problems and other problems as well. So what that means very roughly is that where an object is in the image is not important. Or another way to say it is a shifted image is somehow equivalent to the original image. The label, for example, of the object doesn't change. And in some other problems, like in segmentation, the segmentation mask doesn't change either, except that it's undergoing a shift. So convolutions exploit this translation symmetry through weight sharing. That is to say, they apply the filter in every position using the same set of weights that have to be learned. And therefore, they're more statistically efficient than if you had to learn a filter or a fully connected neuron at for each position. This weight sharing is a good idea because, of course, because of the translation symmetry, a local visual pattern that the filter detects can appear in every location with the same frequency if the symmetry really is perfect. Or at least one can say that if it's useful to detect a feature in one position, then it's also useful to detect it in another position. And finally, equivariance is a good thing because equivariance preserves the symmetry. It's because that the output feature map also undergoes a translation when the input does, that a pattern in the output feature map can also occur at any location. And for that reason, it makes sense to stack multiple convolution layers and thereby exploit the symmetry in each layer of the network. So let's look a bit more detail at this concept of symmetry. So here's a definition. A symmetry is a transformation of some object that leaves the object invariant, or at least leaves some aspect of the object invariant. So we see an example here, a very simple one. We have a triangle, and we can rotate it by 2 pi over 3, and it won't change the object. It will leave the object invariant. And so we say that this rotation is a symmetry of the triangle. Now, in many cases, we're not actually dealing with the object itself, but some description of the object. If we wanted to store a triangle in our computer, we might do it by storing 3 coordinates, x and y coordinates for the 3 corners, and they're stored in some order in our computer memory. So we have that description, and when we apply this rotation to each of the coordinates, for example, we get new coordinates, and they're different. They're different from the originals. So even though the thing that we actually care about may be the triangle itself, which did not undergo a change. And so we can also say that the symmetry is a transformation of the description of an object that gives you an alternative description of the same object. And when that happens, of course, if we apply a neural network to this input, we need that the neural network should process these different or equivalent representations or encodings of the same thing equivalently. So this concept of symmetry can be understood in a much more abstract way. In mathematics, for instance, one can consider the symmetries of many kinds of abstract objects. In physics, one considers the symmetries of a physical system. And also in machine learning, we have many examples. So here are 2 of them. The first one is in computer vision. We've already talked about that. There might be many kinds of transformations that leave some aspect of the image invariant, such as the class label or the identity of the person in this image, for example. And when we know about those kinds of transformations, about those symmetries, it can help with learning. In other cases, like graph neural nets, the second definition applies. Here we really can think of one underlying object, a graph, that has many different encodings. So graph neural networks are becoming increasingly popular. And when you want to build such a thing, you need to think about how do I actually encode the graph so that I can pass it to my neural network. And one way that this is typically done is to encode the graph as an adjacency matrix. So what we do is we order the vertices in some arbitrary way, and then we build an adjacency matrix by putting a 0 in row I, column J, if there's no connection between node I and J in the graph, and a 1 otherwise if there is a connection. Now, because this ordering of the nodes is arbitrary, we can choose a different one and build an adjacency matrix again. And that adjacency matrix will be related by a simultaneous permutation of the rows and columns of the original adjacency matrix. So when we apply a neural network to this adjacency matrix to produce some output, maybe a classification of the graph, then we want that neural network to process these two encodings, the same graph, in an equivalent manner. And that's what equivariance allows you to do. So more generally, we can understand the role of symmetry in learning as follows. We're going to consider the symmetries of a label function. So we'll assume that we have some input space X and some output space Y, say a space of labels or something else. And we have a ground truth function L from X to Y that we're trying to imitate with our neural network. And we'll have some transformation G that maps from X to X, so that maps the input space onto itself. And we say that this transformation is a symmetry of the label function if it satisfies this equation. If applying G first and then L is the same as just applying L. Or in other words, the label of any image is the same as the label of the transformed image. In diagrammatic form, you can see the same thing shown on the right. If we start in the top left at the space X, and then apply G first and then L, we end up in the same place in Y as if we just applied L right away. Now, what we're going to do now is we're going to observe a couple very basic facts about the set of all symmetries of a certain object. And then we're going to basically encode those properties as axioms, and we'll say that an object or a set of transformations that satisfies these properties or axioms, we'll call that a group. So first observation is that if we consider any object, the identity transformation is a symmetry. Symmetry is something that doesn't change the object, so the identity by definition doesn't change anything. So that's a symmetry. That's always part of the symmetry group of this object. Secondly, if we have two transformations that leave an object invariant, then clearly their composition is also a symmetry. It also leaves the object invariant. So we say that a symmetry group is closed under composition. And third, a symmetry should better be invertible because we assume it doesn't change the object. If it's not invertible, it loses some information about the object. And so it couldn't be symmetry. Symmetries are invertible. And furthermore, the inverse of any symmetry is also a symmetry. It also doesn't leave the object invariant. If we rotate our image to the right and rotate it back, if one is a symmetry, then the other is also a symmetry. So the group is closed under inverses. So those are three very basic axioms: identity, closure under composition, and inverses that together define what a group is. And from these very basic axioms, actually a very, very rich theory emerges. You could spend your whole life just studying groups. So there are many kinds of groups where the basic axioms of the group are combined with other types of structure, such as topological structure or smooth manifold or differentiable structure. And at a very high level, we can divide the groups that we're interested in into a couple categories. First of all, we have discrete and continuous groups, also among continuous groups, there are differentiable or smooth groups, Lie groups. Within the discrete groups, one can consider the finite groups, like the symmetries of the triangle. There are 3 rotational symmetries, so that's called the cyclic group with 3 elements, C3. Or you can include reflections as well, then you get D3. You can consider the very large finite group Sn of permutations of n objects. There are also countably infinite groups, discrete groups, like the integer translations, or integer translations in 2D combined with rotations by multiples of 90 degrees, i.e. the symmetries of a grid, a square grid. On the continuous side, we can subdivide into compact groups, like the groups of rotations and reflections, SON and ON. Also, non-compact but locally compact groups, like continuous translations and rotations, and many examples. So the distinguishing, at a very intuitive level, the distinction between compact and locally compact that you can think of is that within the locally compact groups, there can be transformations that sort of get infinitely large. There's no largest translation, for example, but with rotations, you will get back to where you started. So it's a compact group. So of course, there's a formal definition as well, but this is just to give you a very rough sense. There are also groups that are not even locally compact, meaning that for any point, there isn't even a neighborhood that's compact, such as the group of diffeomorphisms, which is infinite dimensional. So those are very difficult to handle. For anything locally compact, there's a fairly nice mathematical theory. Now, for all of these groups, there can be commutative, and they can be non-commutative. Commutative means that the order in which you apply the transformations doesn't matter. So AB is the same as BA. This is, for example, the case in 2-dimensional rotations. If you rotate by some angle and then another angle, the result is the sum of the rotation by the sum of these 2 angles, which doesn't depend on the order. If you rotate around different axes in 3D, however, then already things become non-commutative. And in general, non-commutative groups are much more difficult to understand. All right, so let's look at how knowledge about a symmetry group can help with learning. So here we see some input space, sort of a cartoon picture with a couple points that correspond to images of different letters in different fonts. And we consider the group of rotations by multiples of 90 degrees, C4, so it has 4 elements. And what we can see here is that this group action partitions the input space into so-called orbits. So the orbit of a point X, so one of these images, is just a set of all points that you can get by applying transformations from the group to this point X. So it will always include X because the identity transformation is in the group, and potentially it will include some other elements as well. In this case, all the orbits have size 4, the same size as the group, but that's not true in general. For example, if you have a letter O that's perfectly symmetric, rotationally symmetric, then applying any rotation will just map it back onto itself. And so that would be an orbit of size 1. Now, if this group is a symmetry of our learning problem, what that means is that each orbit will be mapped entirely to one output point. So in this case, we're doing binary classification. So another way to say that is that all the points in one orbit will have the same label. And so you can already see that this should greatly simplify the learning problem, because now we don't have to learn the label for every point, but for every orbit. And there are far fewer orbits in general. Another way to think about this is in terms of equivalence relations. So we can define an equivalence relation among the input points, X and Y, for example. We'll say that X is G equivalent to Y if there is a group element little g in our group big G, such that Gx equals Y. And we can see that this is indeed an equivalence relation because of the actions of the group G that we just looked at before. So an equivalence relation should satisfy reflexivity, that is to say, X should be equivalent to itself. And this is true because of the identity axiom of the group. So G contains the identity transformation, so X will always be G equivalent to itself. Transitivity means that if X is G equivalent to Y and Y is G equivalent to Z, then X is G equivalent to Z. And this is the case because of the closure under composition. Symmetry axiom is also satisfied. If X is G equivalent to Y, then Y is G equivalent to X because of the closure under inverses. All right, so if we have a group acting on our input space, it partitions the space into orbits, which we can think of as equivalence classes, with all of the points in one orbit being G equivalent to each other. And if we know about such orbits or equivalence relation, then that should simplify our learning problem. So you might think then that a way to exploit this knowledge is to just build an invariant representation, to do some kind of pre-processing on your data or to learn some representation that maps all the points in one orbit to a single point in a new feature space. And that's an idea that has been around for a long time and has been tried in many ways with various degrees of success. And although this is useful in some contexts, it has limitations, as shown by this picture. So this is what we call the Picasso problem. So let's say we're trying to understand this image using a neural network. And we know that to recognize, for example, a face or to detect it, it's useful to first detect parts. That's why we have deep networks with multiple layers, where the early layers detect local patterns, then mid layers detect object parts, and later layers detect the whole object in terms of those parts. So when we do that, if we might think that the early layers should be invariant to symmetry transformations, because that would make the learning problem easier for the later layers. They don't have to deal with the variation in position and orientation of the parts, of the eyes and the nose and the mouth and so on. But the problem with that is that if you lose this information about the pose, then it will be difficult for the later layers to see if the different parts are in the right relative pose. And so such a network that is built on top of an invariant representation of eyes, noses, and mouths could not detect that something funny is going on in this image, because all it can do is analyze a bag of features, essentially. So we don't want premature invariance, and that's the reason why equivariant networks have become so popular. So if we're going to have an equivariant network, we will have to have, for our single group of symmetries, we'll have to have it act on the feature space at on each feature space in our network. And what we'll consider is linear group actions, or so-called group representations. That would seem to be a restriction, but actually group representations capture a very large class group of actions that occur in real life problems, including most of the groups acting on signals such as images and audio signals and so on. So what is a group representation? So formally, a group representation rho is a mapping from our group to a set of invertible n-by-n matrices. Or if you have a representation in an abstract vector space, which could also be infinite dimensional, then it will map to the set of invertible linear operators on this space. And we say that rho is a representation if it satisfies this property on the right, which says that if we have two group elements, G and H, and we compose them first in the group using the group composition law, and then we use rho to get our representation matrix, that should be the same as first getting the representation matrices for the individual elements and then applying matrix multiplication to those. So let's look at some examples. The first one is graph features. So we'll define a graph feature as a representation of the symmetric group Sn, the group of permutations of n nodes, the nodes of our graph. And we'll look at three different representations. So the first one is called the trivial representation, which is something you might use for the output of the network if you're doing graph classification. So the trivial representation, what it does is it takes any permutation P, for example, P12, which swaps the first and second node of the graph. And whatever permutation it is, it will map it to the number 1. So it's a representation on a one-dimensional vector space, just a real line. And it's trivial in the sense that it maps every permutation to the number 1. You can see that it still satisfies the axiom of being a representation. For any two permutations, you compose them, compute the representation, well, that's 1. And you compute the representation of the two individual permutations. Those are also 1. You multiply the ones and you get 1, so it's all the axiom is satisfied. So this gives you an invariant quantity, which is useful if you're doing graph classification. You want the classification of the graph to not depend on the order of the nodes. But in the input and maybe the intermediate layers of your network, you might want to have some equivariant features. For example, you might want to associate one number with each node in the graph, some node feature. Well, such a node feature, of course, transforms by, if you apply a permutation to the nodes, then these node features, they transform with it, they will also get permuted. So the representation rho 1 of P is just a permutation matrix multiplied by this vector. So the coefficients of the vector get swapped. And finally, we can consider a tensor feature. So for example, the adjacency matrix that we looked at in one of the earlier slides, that's an example of a 2 tensor. And the way that it transforms is that if we apply a certain permutation to the order of the nodes, then both the rows and the columns will be permuted. So if P is our permutation, it acts on a matrix M as PM P transpose. And you can check that this also satisfies the axioms of a group, and you can also write this, of course, in flattened matrix vector form. So there are many graph networks, some based on message passing, and some actually based on this kind of understanding, although the use of representations is still not very common in the literature. So another example is translation of one-dimensional signals. So here our group will be the group of integers under addition. So an integer is a well, you can think of it as a translation, and composition means just adding these integers. To make that act on a space of signals, we need a representation. So we consider the space of one-dimensional signals with 5 samples, just for simplicity, and we'll assume periodic boundary conditions. Then the representation rho of the integer n is just a matrix that will cyclically shift the coefficients by 1 step raised to the power n. And so rho 1 times this vector gives you the same vector, but with all the coefficients shifted by 1 in a cyclic manner. All right, then now we have everything to state the general setup that you work with in an equivariant network. This was first considered by Wood and Shaw-Taylor already in 1996. So the basic idea is we have feature spaces, xi, They're vector spaces. And we have maps between them that in the neural network literature called layers. Fi maps from xi minus 1 to xi. We also have a symmetry group G. And for each feature space, we have a group representation rho I of G. And we'll say that this network is equivariant if for all layers and all group elements, it's the case that applying Fi after rho I minus 1 of G is the same as applying rho I of G after Fi. So again, this is shown with a commutative diagram on the left. You can start anywhere and follow the arrows in any order. And if you have two paths that lead to the same end node, then the results should be the same. So starting in x0 on the left and following F1 and then rho 1 of G should be the same as applying rho 0 of G and then F1. And the diagram also makes clear that the composition of equivariant maps gives you an equivariant map. All right, so let's think a bit more about why equivariance is a good property. So we can think of equivariance as symmetry-consistent generalization, as shown in this figure. So here again, we have two input images, X and Y, different letters, different fonts for the letter A, and they lie on an orbit of rotated versions of this image. So somewhere along that orbit, there's the point rho 1 G of X, with G being a rotation, and also rho 1 G of Y. Now let's assume that if we compose the first few layers of our network, we get a map that we call phi. And let's suppose that this map phi has learned that mapping X and Y onto the same feature vector is a good idea for whatever task that it's trained for. So X and Y, the different letter A, they're mapped into a sort of a feature vector representing a generic letter A. And now let's suppose that the network maps the rotated X and Y to different points. Well, that's a situation that cannot occur in an equivariant network because we have two equivariance constraints, one for X and one for Y. The one for X says that if I map X to the latent space and then transform by rho 2, I should get the same thing as first transforming by rho 1 in the input space and then applying the network phi. But this is inconsistent with the second constraint, which says that the same must be true for the point Y. So rho 2 would have to map this same single point that represents the generic A, phi of X, and should map it to two different points in the latent space. But of course, a function can't do that. So this cannot occur. And importantly, it cannot occur anywhere in the input space, including points that you've never seen before. So the network has to generalize in a way that respects the symmetry. Equivalent points are treated equivalently. So one question that we often get is why should we build in equivariance into a neural network when we can just do data augmentation? So the story is complicated. There are pros and cons of different approaches. And I've tried to make an overview here in this table. So first of all, when you build an equivariant net, you're putting a constraint on every individual layer rather than a constraint on the network as a whole. And as such, every layer has to process the data in a way that respects the symmetry. Every layer gets a benefit of parameter sharing and therefore increased statistical efficiency. Whereas with data augmentation, you're essentially only putting a constraint on the network as a whole. Data augmentation is easy to implement. All you have to do with train time augmentation is randomly apply a transformation to your training data point and then do an update. With test time augmentation, the idea is that you apply every transformation in your group, or at least some random sampling if the group is large, and then average the predictions by the network. That's fairly simple as long as you know how to apply the transformation. With equivariance, it depends a bit on what the group is and what approach you take. Some implementations are fairly simple. They merely involve, computing a basis of filters, linearly combining them using some learned parameters, and then applying standard convolutions. Some approaches are more involved, so it can be more difficult to implement. On the other hand, equivariant networks, they are guaranteed to be equivariant, both the training data and the test data, and anywhere in your input space, as I mentioned before. On the other hand, train time augmentation will often fail to be equivariant even at the train data, because the network doesn't get to see every training point with every possible transformation during training and actually converge to a perfect equivariant solution. And it certainly doesn't guarantee that the result will be equivariant at test time, because the network just isn't constrained at those points. Equivariance can also work for large groups, like the group of permutations with n factorial elements, or even infinite groups like continuous translations and rotations. All of these methods are efficient at train time. With equivariant networks, it's the case that because of the increased statistical efficiency, you can often make the network bigger. That will make it also slower to do a forward pass. But what we have found, at least for certain class of equivariant networks, namely group convolutional networks, is that the convergence is also much more efficient, up to 10x faster in terms of number of steps needed to converge. In terms of test time efficiency, train augmentation is the most efficient. It doesn't change anything to the inference time. Test time augmentation can be slow or very slow depending on the size of the group. And equivariant nets, they typically are not much more inefficient than a standard neural net. In fact, often you can convert an equivariant convolutional net to a plain convolutional net by doing the filter expansion step once after training, and then you just have a regular convnet. But it might be a bit bigger if you choose to make it bigger because of reduced overfitting. Another approach that is sometimes offered as an alternative is something you can call canonicalization. So the basic idea is we have our inputs, say images, and we can all put them in a canonical pose. So this is actually an example of an invariant representation, and so it suffers from the problems that I mentioned before. But to go into a bit more detail, one of the problems with this is that the mapping that assigns a pose to an image is actually discontinuous. So take this example. We have 4 O's that are all close to a perfect circle. If we consider this perfect circle, we can ask what pose does it have? What rotational pose? What is its angle? Well, we have to choose something, so we'll say, let's call that angle 0. But of course, not all 4 of these almost symmetric circles, or almost perfectly symmetric circles, can have an angle that's close to 0. So that mapping is actually discontinuous.